Picture this. Right now, as you're watching this video, there are over 400 billion stars in our galaxy alone, each one potentially hosting planets. Some of those planets might have oceans, some might have atmospheres, and some might have life. But here's the mind-bending question that's kept scientists awake at night for decades. If the universe is so vast and so full of possibilities, where is everybody? Welcome to Aether Theory. Sit back, relax, and enjoy. You're about to embark on a journey that will take you from the deepest trenches of our own oceans to the farthest reaches of space, from ancient microbes that survived impossible conditions to cutting-edge telescopes that can peer into the atmospheres of worlds thousands of light years away. We're going to explore one of the most profound questions humanity has ever asked. Are we alone? But before we dive in, let me tell you something that might shock you. The answer to this question might fundamentally change everything we think we know about our place in the universe. And we might be closer to finding that answer than you think. Let's start with a story that will give you goosebumps. In 1977, a scientist named Jerry Emmon was working late at night at the Big Ear Radio Telescope in Ohio. The facility looked nothing like what most people imagine when they think of a radio telescope. No giant dish pointing at the sky, but rather a field of metal reflectors and receivers that had been listening to the cosmos for years as part of SETT, the search for extraterrestrial intelligence. On August 15, 1977, at 11:16 p.m. Eastern Time, something extraordinary happened. The telescope detected a signal so powerful, so perfectly positioned in the radio spectrum, and so unlike anything natural that Eamon grabbed a red pen and wrote, "Wow!" in the margins of the computer printout. That simple exclamation would become one of the most famous annotations in the history of science. The signal lasted exactly 72 seconds, the maximum time the Big Ear telescope could observe any point in the sky as Earth's rotation carried it across the receiver's field of view. It came from the direction of the constellation Sagittarius, near the star cluster M55. The signal's frequency was 1/420.556 MHz, incredibly close to the hydrogen line, the natural frequency at which hydrogen atoms emit radio waves, and a frequency that astronomers had long theorized would be an obvious choice for any civilization trying to communicate across the galaxy. But here's what made the wow signal so tantalizing. Its characteristics matched almost perfectly what scientists had predicted an artificial extraterrestrial signal would look like. It was narrow-band, meaning it occupied a very specific frequency rather than being spread across a broad range like natural cosmic phenomena. It showed no signs of being Doppler shifted, which would be expected if it came from a planet orbiting a star. And its intensity was enormous, about 30 times stronger than the background noise of deep space. When Emmon first saw the printout, he was so startled that he immediately called his colleague, Bob Dixon, even though it was nearly midnight. The two men spent the rest of the night analyzing the data, checking for instrumental errors, satellite interference, or any other explanation for what they had detected. They found none. The next night, they pointed the telescope back toward the same spot in the sky. Nothing. The night after that, still nothing. For weeks, months, and then years, they continued to monitor that region of space. The signal never returned. Despite decades of subsequent observations with increasingly sophisticated equipment, no one has ever detected the wow signal again. Was it aliens trying to contact us? Was it some unknown natural phenomenon? Was it a one-time technological transmission from a distant civilization? Or was it something else entirely? Perhaps a signal that was actually terrestrial in origin but appeared to come from space due to some unusual propagation effect? We still don't know, and that uncertainty has made the wow signal one of the most famous unsolved mysteries in astronomy. But here's what's fascinating about the wow signal. It wasn't the beginning of our search for alien life. It wasn't even close. The question of whether we're alone in the universe has haunted humanity for millennia, driving some of our greatest thinkers to contemplate the possibility of life beyond Earth. The ancient Greek philosopher Democritus, who lived in the 5th century BCE, proposed that the universe contained infinite worlds, many of which might be inhabited. His contemporary Epicurus wrote, "There are infinite worlds, both like and unlike this world of ours. We must believe that in all worlds there are living creatures and plants and other things we see in this world. Even Aristotle, despite his belief that Earth was the center of the universe, pondered the possibility of life elsewhere. In his work, On the Heavens, he wrote about the potential for other worlds to exist, though he ultimately concluded that Earth was unique. During the Renaissance, as our understanding of the cosmos expanded, so did speculation about extraterrestrial life. Giordano Bruno, the Italian philosopher who was burned at the stake in 1600, partly for his heretical views about the universe, argued that the stars were distant suns, each potentially surrounded by planets that might harbor life. In the 1600s, astronomers like Christian Huygens and Giovanni Cassini speculated about life on other planets in our own solar system. Huygens wrote extensively about the possibility of life on Mars and other worlds, reasoning that if God had created life on Earth, he would surely have done the same elsewhere. The invention of the telescope in the early 17th century gave new impetus to these speculations. When Galileo first observed the moon through his primitive telescope in 69, he saw mountains, valleys, and what he thought might be seas. If the moon had geography similar to Earth, might it not also have inhabitants? As telescopes improved, astronomers began to map the surface features of Mars in detail. In 1877, Italian astronomer Giovanni Schiaparelli observed what he called canali, channels, on the Martian surface. When this was translated into English as canals, it sparked widespread speculation that Mars might be home to an intelligent civilization that had built an extensive irrigation system. This speculation reached its peak with American astronomer Percival Lowell, who established an observatory in Arizona specifically to study Mars. Lowell became convinced that the supposed canals were evidence of a dying Martian civilization desperately trying to transport water from the polar ice caps to their cities near the equator. He wrote several books about his observations, including Mars and its Canals and Mars as the Abode of Life, which captured the public imagination and convinced many people that Mars was indeed inhabited. Of course, we now know that Lowell's canals were optical illusions, tricks of the eye and limitations of his telescopes that made him see linear features that didn't actually exist. But his work was important because it represented the first systematic scientific attempt to search for evidence of extraterrestrial intelligence. The modern era of the search for extraterrestrial life began in the 20th century as our understanding of physics, chemistry, and biology advanced to the point where we could make educated guesses about where life might exist and how we might detect it. In 1950, the physicist Enrico Fermi posed a question during a casual lunch conversation at Los Alamos National Laboratory that would become known as the Fermi Paradox. Fermi and his colleagues were discussing recent UFO sightings when Fermi suddenly asked, "Where is everybody?" What Fermi was getting at was a fundamental contradiction. On one hand, the universe is vast and ancient. Our galaxy alone contains hundreds of billions of stars, many of which are older than our Sun. Even if only a tiny fraction of stars have planets, and only a tiny fraction of planets develop life, and only a tiny fraction of those develop intelligent life, the sheer number of possibilities should mean that intelligent civilizations are common. Moreover, any civilization that develops space travel could, in principle, spread throughout the galaxy in just a few million years, a blink of an eye in cosmic terms. Even traveling at a modest fraction of the speed of light, or sending self-replicating probes to colonize distant star systems, an expanding civilization could reach every corner of the galaxy relatively quickly. So where are they? If the galaxy should be teeming with life, why don't we see any evidence of it? This question became even more pressing in 1961 when astronomer Frank Drake organized the first modern conference on the search for extraterrestrial intelligence. Held at the National Radio Astronomy Observatory in Green Bank, West Virginia, the conference brought together some of the most brilliant minds of the time, including Carl Sagan, Melvin Calvin, and Philip Morrison. To focus the discussion, Drake developed what became known as the Drake equation, not really an equation in the mathematical sense, but rather a framework for thinking about the factors that might determine how many communicating civilizations exist in our galaxy at any given time. The Drake equation considers 7 factors. the rate of star formation in the galaxy, the fraction of stars that have planets, the average number of planets per star that could potentially support life, the fraction of those planets where life actually develops, the fraction of life-bearing planets where intelligent life evolves, the fraction of intelligent civilizations that develop technology capable of interstellar communication, and the average length of time such civilizations remain detectable. When Drake first plugged numbers into his equation, he estimated that there might be somewhere between 1,000 and 100,000 communicating civilizations in our galaxy. Carl Sagan, ever the optimist, suggested the number might be even higher, perhaps millions of civilizations. But here's the problem. Even the most conservative estimates suggested that there should be thousands of detectable civilizations in our galaxy. Yet, when Drake and his colleagues began the first systematic search for extraterrestrial radio signals, they found nothing but cosmic silence. This silence has persisted for more than 6 decades since Drake's first observations. We've searched thousands of star systems, monitored millions of radio frequencies, and deployed increasingly sophisticated detection equipment. We've looked for narrowband signals, broadband transmissions, pulsed signals, and continuous waves. We've searched for signals that might be intentional communications and for the accidental radio leakage that would inevitably surround any technological civilization. And with very rare exceptions like the tantalizing "wow" signal, we found nothing. This absence of evidence has led to numerous proposed solutions to the Fermi Paradox, each more thought-provoking than the last. Perhaps intelligent life is incredibly rare and we're one of the few, or perhaps the only, technological civilizations in the galaxy. This possibility, sometimes called the rare Earth hypothesis, suggests that the development of complex life requires such a precise set of conditions that it occurs only very rarely. Perhaps most civilizations destroy themselves shortly after developing the technology for interstellar communication. Nuclear weapons, climate change, resource depletion, or some other catastrophe might claim most technological species before they have a chance to spread beyond their home worlds. Perhaps advanced civilizations deliberately hide from younger species like ourselves. This zoo hypothesis suggests that we might be living in a kind of cosmic nature preserve, observed but not contacted by more advanced beings who have agreed not to interfere with our development. Perhaps truly advanced civilizations transcend physical existence entirely, uploading their consciousness into computer systems or evolving into forms of life that are so different from us that we wouldn't recognize them as intelligent even if we encountered them. Or perhaps, and this is perhaps the most unsettling possibility, there's a great filter somewhere ahead of us, some challenge or catastrophe that prevents most civilizations from surviving long enough to become a spacefaring species. The Great Filter hypothesis, proposed by economist Robin Hanson, suggests that there's some step in the evolution from simple organic compounds to a galaxy-spanning civilization that's incredibly difficult to pass. If this filter is behind us, if it was the emergence of life itself, or the development of complex cells, or the evolution of intelligence, then we might be one of the lucky few species to have made it this far. But if the Great Filter is ahead of us, if it's something that happens to civilizations at our current level of development, then our future might be much more precarious than we realize. Maybe the reason we don't see evidence of alien civilizations is because most of them don't survive the transition from a planetary to a spacefaring species. These are sobering thoughts, but they've also motivated an intensification of our search efforts. If we are alone, or nearly alone, then Earth and everything on it becomes incredibly precious, the only known repository of life and intelligence in a vast, cold universe. But if life is common, and we're just not looking in the right way or in the right places, then we need to expand and improve our search strategies. The search for extraterrestrial intelligence has evolved dramatically since Drake's pioneering observations in 1960. Modern SETI projects use radio telescopes that are orders of magnitude more sensitive than anything available in Drake's time. They can search millions of frequency channels simultaneously and monitor thousands of star systems at once. Projects like Breakthrough, Listen, funded by Russian billionaire Yuri Milner, represent the most comprehensive search for extraterrestrial intelligence ever undertaken. Using some of the world's most powerful radio telescopes, including the 100-meter Green Bank telescope in West Virginia and the 64-meter Parkes telescope in Australia, Breakthrough Listen is scanning millions of stars across a broad range of radio frequencies. But the modern search for extraterrestrial life isn't limited to radio astronomy. Scientists are also looking for optical signals, brief flashes of laser light that might represent attempts at interstellar communication. They're searching for infrared signatures that might indicate the presence of massive artificial structures around distant stars. They're even looking for patterns in the cosmic microwave background radiation that might represent messages encoded in the fundamental structure of the universe itself. And the search isn't limited to intentional communications. Scientists are also looking for techno-signatures, evidence of alien technology that might be detectable even if it wasn't intended to communicate with us. Industrial pollution in the atmosphere of an exoplanet, for example, would be a clear sign of technological activity. Artificial lights on the night side of a distant world might indicate urban areas. Massive solar collectors or other megastructures around a star would create distinctive patterns in the star's light output. Some of these ideas might sound far-fetched, but they're based on solid scientific reasoning. Any sufficiently advanced technological civilization would inevitably modify its environment in ways that might be detectable across interstellar distances. The challenge is developing instruments sensitive enough to detect these modifications and clever enough to distinguish artificial signatures from natural phenomena. But while we're searching for evidence of advanced alien civilizations, we're also pursuing a parallel track that might be even more promising: the search for simple life in our own solar system and beyond. The discovery of any form of life beyond Earth, even simple microbes, would be one of the most profound discoveries in human history. It would tell us that life is not unique to Earth, that the processes that led to the emergence of biology here can occur elsewhere. And if life can emerge independently in multiple locations, then the universe might be teeming with biological activity, even if most of it hasn't yet evolved to the level of intelligence and technology. This realization has led to the development of astrobiology, a new scientific discipline that combines astronomy, biology, chemistry, geology, and other fields to study the possibility of life in the universe. Astrobiologists don't just look for life as we know it, they also try to understand the fundamental principles of biology and to imagine how life might evolve under different conditions. One of the key insights of astrobiology is that life on Earth exists in an astonishing variety of extreme environments. Deep-sea hydrothermal vents, where water temperatures exceed 750 degrees Fahrenheit and toxic chemicals abound, host thriving ecosystems. Highly acidic hot springs, Antarctic ice sheets, the depths of underground mines, and even the upper atmosphere, all of these environments that were once thought to be completely sterile, have been found to harbor life. These discoveries have revolutionized our understanding of habitability. If life can survive and thrive in such extreme conditions on Earth, then the number of potentially habitable environments in the universe is far larger than we ever imagined. Mars, for example, was once thought to be a cold, dry, lifeless world, but we now know that it once had a thick atmosphere and liquid water flowing across its surface. Even today, there's evidence of subsurface water and possibly active geological processes. The discovery of organic compounds in Martian rocks and seasonal variations in atmospheric methane suggest that Mars might still harbor life, perhaps deep underground where it's protected from the harsh surface conditions. Similarly, the icy moons of the outer solar system, worlds like Europa, Enceladus, and Titan, were once thought to be frozen wastelands. But we now know that several of these moons harbor subsurface oceans that contain more water than all of Earth's oceans combined. These hidden seas might be among the most habitable environments in the solar system. And beyond our solar system, we've discovered thousands of exoplanets, many of which orbit in the habitable zones around their stars, regions where temperatures are suitable for liquid water to exist on planetary surfaces. Some of these worlds appear to be remarkably Earth-like, with similar sizes, compositions, and orbital characteristics. The discovery of potentially habitable exoplanets has opened up new possibilities for detecting alien life through atmospheric analysis. Life has a profound effect on planetary atmospheres, and these biosignatures might be detectable across interstellar distances with sufficiently powerful telescopes. On Earth, for example, our atmosphere contains about 21% oxygen, a highly reactive gas that would quickly disappear unless it was being continuously replenished by photosynthetic organisms. The simultaneous presence of oxygen and methane in our atmosphere is particularly telling, since these two gases react with each other and would quickly be depleted unless something was actively producing both. If we could detect similar atmospheric disequilibria around other worlds, it would be strong evidence for biological activity. And with new generation space telescopes like the James Webb Space Telescope, we're finally developing the capability to analyze the atmospheres of Earth-sized exoplanets in detail. But perhaps the most exciting development in the search for alien life is the growing realization that we might not have to wait for some future breakthrough to find our answer. The evidence might already be sitting in laboratories around the world, waiting to be properly analyzed and understood. NASA's Perseverance rover is currently collecting samples of Martian rock and soil, carefully storing them in sealed tubes for eventual return to Earth. When those samples finally arrive in terrestrial laboratories sometime in the 2030s, we'll be able to analyze them with instruments far more sophisticated than anything we can send to Mars. If Mars ever harbored life, even briefly, even billions of years ago, traces of that life might still be preserved in these samples. Fossilized microbes, distinctive isotopic signatures, or complex organic molecules that can only be produced by biological processes could provide definitive evidence that life once existed on our neighboring planet. And Mars isn't the only place where we might find evidence of alien life. The Cassini spacecraft flew through the water plumes erupting from Saturn's moon, Enceladus, and detected organic compounds and other chemicals that, on Earth, are associated with life. Future missions to Europa, Enceladus, and other icy moons could directly sample these subsurface oceans, searching for swimming microbes in alien seas. Even Venus, despite its hellish surface conditions, might harbor life in its upper atmosphere, where temperatures and pressures are surprisingly Earth-like. The recent detection of phosphine gas in Venus's atmosphere, a molecule that on Earth is almost exclusively produced by living organisms, has sparked intense debate and follow-up observations. All of these possibilities suggest that we might be on the verge of answering one of humanity's oldest and most profound questions. The search for alien life has never been more active, more sophisticated, or more promising than it is today. But as we stand on the threshold of potentially discovering that we're not alone, it's worth reflecting on what such a discovery would mean. How would it change our understanding of life, intelligence, and our place in the universe? How would it affect our religions, our philosophies, our sense of purpose and meaning? These questions don't have easy answers, but they're becoming increasingly urgent as our search capabilities improve and the possibility of discovering alien life becomes more real with each passing year. The WOW signal remains unexplained more than 4 decades after its detection. But whether it was a message from an alien civilization, an unknown natural phenomenon, or something else entirely, it serves as a reminder that the universe is full of mysteries waiting to be solved. And as we continue our search, as we deploy ever more sophisticated instruments and explore new frontiers, we're driven by the same curiosity that motivated Democritus to speculate about infinite worlds, that led Galileo to point his telescope at the moon, and that inspired Frank Drake to listen for signals from the stars. We're driven by the fundamental human need to understand our place in the cosmos, to know whether we're alone or part of a vast community of life and intelligence that spans the galaxy and perhaps the universe itself. The answer to that question, whatever it turns out to be, will be one of the most important discoveries in human history. And we might not have to wait much longer to find it. Deep beneath the Pacific Ocean, in a place where no ray of sunlight has ever penetrated, something extraordinary is happening. 2.5 miles below the surface, where the crushing pressure would instantly kill any surface-dwelling organism, where temperatures can exceed 750 degrees Fahrenheit, where the water is rich with hydrogen sulfide and other chemicals that would be lethal to most life forms, an entire ecosystem thrives in eternal darkness. This is the world of hydrothermal vents, underwater volcanic chimneys that spew superheated mineral-rich water into the deep ocean. When scientists first discovered these vents in 1977, they expected to find a barren wasteland devoid of life. Instead, they found one of the most vibrant and alien ecosystems on Earth. Giant tube worms, some reaching lengths of over 6 feet, sway in the toxic currents like ghostly white trees in an underwater forest. These creatures have no mouth, no stomach, no digestive system as we understand it. Instead, they harbor billions of bacteria within their bodies, bacteria that convert the poisonous hydrogen sulfide into organic compounds that feed their hosts. Strange, ghostly white crabs scuttle across carpets of bacterial mats that cover the seafloor like alien snow. Fish with antifreeze proteins in their blood cruise through the mineral-rich water, their bodies adapted to survive in conditions that would seem impossible to surface dwellers. Shrimp with no eyes but heat-sensing organs cluster around the vents, feeding on bacteria and each other in a complex food web that depends not on the sun's energy but on the chemical energy of the Earth itself. This discovery revolutionized our understanding of life. Before 1977, scientists believed that all ecosystems on Earth ultimately depended on photosynthesis, the process by which plants and algae convert sunlight into chemical energy. The food webs of the deep ocean were thought to depend on a gentle rain of organic matter falling from the sunlit surface waters above. But the hydrothermal vent communities showed that life could exist independently of the sun. These ecosystems are powered by chemosynthesis, the process by which bacteria convert chemical energy from the vents into organic compounds. It was the first proof that life could exist in environments that are completely cut off from solar energy, depending instead on geochemical processes for their energy source. The implications of this discovery for astrobiology were profound. If life could thrive in the extreme conditions of hydrothermal vents, then similar environments elsewhere in the solar system might also be habitable. The subsurface oceans of moons like Europa and Enceladus, warmed by tidal heating and possibly home to their own hydrothermal systems, suddenly seemed much more promising as potential habitats for alien life. But hydrothermal vents were just the beginning. As scientists began to explore Earth's most extreme environments more systematically, they discovered that life exists in places that challenge our very definition of habitability. In the Atacama Desert of Chile, one of the driest places on Earth, microbes survive inside salt crystals and beneath translucent rocks, extracting moisture from the air and energy from ultraviolet radiation. Some parts of the Atacama receive no measurable rainfall for decades at a time, yet life persists, dormant during the worst conditions and springing back to activity when even the tiniest amount of moisture becomes available. The survival strategies of these desert microbes are nothing short of remarkable. Some species can remain dormant for years or even decades, their metabolism slowed to nearly undetectable levels. When water becomes available, even in the form of brief fog or dew, they can rapidly reactivate, reproduce, and return to dormancy before the moisture disappears. These organisms have developed sophisticated mechanisms for dealing with extreme desiccation. They produce protective compounds that prevent their cellular machinery from being damaged by dehydration. They can repair DNA damage caused by intense ultraviolet radiation. Some species can even photosynthesize using infrared light filtered through their rock substrates, capturing energy from wavelengths that most plants can't use. The Atacama Desert is often used as an analog for Mars because of its extreme dryness, high levels of ultraviolet radiation, and oxidizing soil chemistry. The fact that life can survive in these conditions gives scientists hope that similar organisms might exist on Mars, perhaps in subsurface environments where they're protected from the harshest surface conditions. But even the Atacama seems hospitable compared to some of the other extreme environments where life has been found. In South Africa's Mponeng gold mine, scientists have discovered bacteria living more than 2 miles beneath the surface in an environment that has been cut off from the surface world for millions of years. These deep subsurface organisms, dubbed intraterrestrials by some researchers, survive in complete darkness, feeding on hydrogen gas produced by the radioactive decay of uranium in the surrounding rocks. The water they live in is ancient. Some of it hasn't seen the surface for hundreds of millions of years, long before complex life evolved on Earth. The discovery of this deep biosphere has profound implications for astrobiology. If life can exist kilometers beneath Earth's surface, depending only on chemical energy from radioactive decay, then similar life might exist in the deep subsurface of Mars, Europa, or other worlds where surface conditions are too harsh for life as we know it. The deep biosphere might actually be one of the largest habitats for life on Earth. Scientists estimate that the total mass of microbes living in Earth's subsurface might rival or exceed the mass of all surface life combined. This hidden world of bacteria and archaea extends from just below the surface to depths of several kilometers, wherever liquid water can exist and chemical energy is available. Some of these deep-dwelling organisms are among the most primitive life forms on Earth, representing lineages that split off from the tree of life billions of years ago. Studying them gives us insights into what early life on Earth might have been like and what the first life forms on other worlds might resemble. But perhaps the most extreme environment where life has been found is in the highly acidic hot springs of places like Yellowstone National Park. The Grand Prismatic Spring, with its stunning rainbow of colors, owes its beauty to communities of thermophilic bacteria and archaea that thrive in water temperatures approaching the boiling point. Different species of these heat-loving microbes have different optimal temperature ranges, creating distinct bands of color as you move from the hottest center of the spring to the cooler edges. Some species thrive at temperatures above 200 degrees Fahrenheit, living in water so hot it would cook most life forms instantly. These thermophiles have evolved remarkable adaptations to survive in such extreme heat. Their proteins are stabilized by additional chemical bonds that prevent them from unfolding at high temperatures. Their cell membranes are composed of special lipids that remain intact even when the water around them is nearly boiling. Some species even require high temperatures to survive. They literally cannot live in cooler conditions. The study of thermophiles has practical applications beyond astrobiology. Many of the enzymes used in biotechnology, including the TARC polymerase enzyme essential for PCR testing, come from thermophilic organisms. These heat-stable enzymes are valuable tools for industrial processes, medical diagnostics, and research applications. But for astrobiologists, thermophiles are important because they expand our understanding of the temperature limits for life. If organisms can survive in boiling water on Earth, then the hot springs that might exist on Mars, or the hydrothermal systems suspected to exist in the subsurface oceans of icy moons, might also support life. Even more extreme are the psychrophiles, organisms that thrive in extremely cold conditions. In Antarctica, scientists have found bacteria living in subglacial lakes that have been isolated from the atmosphere for millions of years. These lakes, buried beneath miles of ice, are kept liquid by geothermal heat from below and the insulating effect of the ice above. Lake Vostok, the largest of these subglacial lakes, has been sealed beneath the Antarctic ice sheet for at least 15 million years. When Russian scientists finally drilled through the ice to reach the lake in 2012, they found evidence of microbial life in this ancient, isolated ecosystem. The organisms living in Lake Vostok and similar subglacial environments face multiple challenges: near freezing temperatures, complete darkness, extreme isolation, and limited nutrients. Yet they somehow managed to survive and maintain viable populations for millions of years. These psychrophilic organisms have evolved sophisticated anti-freeze mechanisms to prevent ice crystals from forming inside their cells. They produce special proteins and other compounds that lower the freezing point of their cellular fluids. Their metabolisms are extremely slow, allowing them to survive on minimal energy inputs for extended periods. The discovery of life in subglacial lakes has important implications for astrobiology, particularly for our understanding of potential habitats on Mars and the icy moons of the outer solar system. If life can survive for millions of years in the isolated, frigid environment of subglacial lakes, then similar environments elsewhere in the solar system might also be habitable. But perhaps the most mind-blowing discovery in extremophile research came in 2000 when scientists announced that they had successfully revived bacteria that had been dormant for 250 million years. These ancient microbes were found trapped in salt crystals from the Permian period, long before dinosaurs walked the Earth. The bacteria, belonging to a species called Bacillus permians, were embedded in salt deposits that formed in an ancient sea. When the researchers carefully extracted the organisms from their crystal prisons and placed them in nutrient-rich media, the bacteria began growing and reproducing as if they had just taken a very long nap. This discovery challenged everything scientists thought they knew about the limits of life's longevity. How could organisms remain viable for so long? The answer seems to lie in the extremely stable environment inside salt crystals, which protect the bacteria from radiation, temperature fluctuations, and chemical damage. The implications for astrobiology are staggering. If microbes can remain viable for hundreds of millions of years in salt crystals, then any planet or moon with salt deposits might potentially harbor ancient life forms. Mars, for example, shows extensive evidence of ancient salt deposits formed by evaporating lakes and seas. Could these deposits contain preserved Martian life from billions of years ago? But extremophiles aren't just survivors, they're also innovators. Many of these organisms have evolved unique metabolic pathways that allow them to extract energy from sources that other life forms can't use. Some bacteria can breathe metals instead of oxygen using iron, manganese, or even uranium as electron acceptors in their metabolic processes. Others can survive on incredibly simple diets, extracting all the nutrients they need from nothing more than rock and water. Some species of bacteria can literally eat rocks, breaking down minerals to extract the energy and nutrients they need to survive. One group of organisms, the methanogens, produces methane as a byproduct of their metabolism. These archaea are found in environments ranging from deep-sea sediments to the guts of animals, and they play a crucial role in Earth's carbon cycle. Interestingly, methane has been detected in the atmosphere of Mars, leading some scientists to speculate that Martian methanogens might be responsible for at least some of this gas. The diversity of metabolic strategies found among extremophiles suggests that life is incredibly creative in finding ways to extract energy from the environment. This metabolic flexibility means that life might be possible in a much wider range of environments than we previously thought. For example, some bacteria can photosynthesize using infrared light instead of visible light, allowing them to harvest energy from heat radiation. Others can use the energy of cosmic radiation to power their metabolism. Some species can even survive in the vacuum of space, protected by special proteins and repair mechanisms that fix radiation damage to their DNA. The study of extremophiles has also revealed that the boundaries between the three domains of life, bacteria, archaea, and eukaryotes, are more blurred than scientists once thought. Many extremophiles are archaea, a group of organisms that were only recognized as distinct from bacteria in the 1970s. Archaea are particularly well represented in extreme environments, and they've evolved some of the most remarkable adaptations to hostile conditions. Some archaea can thrive in environments so acidic they would dissolve metal with pH levels below 0. Others live in salt concentrations so high that they would pickle any other organism. One group of archaea, the hyperthermophiles, holds the current record for surviving the highest temperatures of any known life form. The species, strain 121, can survive autoclaving at 250 degrees Fahrenheit, temperatures that would sterilize any medical instrument. Another species, Pyrolobus fumari, can grow at temperatures up to 235 degrees Fahrenheit. These temperature extremes are important for astrobiology because they expand our understanding of where life might be possible on other worlds. Venus, for example, has surface temperatures of over 860 degrees Fahrenheit, far too hot for any known life form. But if life could somehow evolve even greater temperature tolerance, or if cooler microenvironments exist on Venus, life might be possible even on our hellish neighboring planet. The study of extremophiles has also revealed that life can exist in environments with radiation levels that would be lethal to humans. The bacterium Deinococcus radiodurans can survive radiation doses 1,000 times higher than would kill a human. It does this through remarkably efficient DNA repair mechanisms that can reconstruct its genome even after it's been shattered by radiation. This radiation resistance is particularly relevant for astrobiology because space is a high radiation environment. Any life that evolved on planets with thin atmospheres or weak magnetic fields would need to deal with much higher radiation levels than life on Earth experiences. The existence of radiation-resistant organisms suggests that such adaptations are possible. Some extremophiles can even survive in space itself. In 2008, European scientists exposed samples of the lichen species Rhizocarpon geographicum to the vacuum of space for 15 days. When the samples were returned to Earth, they showed no signs of damage and resumed normal biological activity. Other experiments have shown that various bacteria, fungi, and even some animals, like tardigrades, can survive exposure to space conditions. These organisms use a variety of strategies to cope with the vacuum, radiation, and temperature extremes of space, including entering dormant states, producing protective compounds, and rapidly repairing radiation damage. The ability of life to survive in space has important implications for the panspermia hypothesis, the idea that life might be able to travel between planets or even between star systems. If organisms can survive the journey through space, either as hitchhikers on meteorites or as passengers on spacecraft, then life might be able to spread throughout the solar system or even the galaxy. But extremophiles aren't just important for understanding where life might exist, they're also changing our understanding of what life is. The diversity of metabolic strategies, environmental tolerances, and survival mechanisms found among extremophiles suggests that life is far more flexible and adaptable than we once thought. This flexibility has led some scientists to propose that we might need to revise our definition of life itself. Traditional definitions focus on characteristics like metabolism, reproduction, and response to stimuli. But extremophiles challenge these definitions by exhibiting forms of life that operate at the very limits of what we consider possible. Some extremophiles, for example, can remain dormant for thousands or even millions of years, showing no detectable signs of metabolism or activity. Are these organisms alive during their dormant periods? They retain the potential for life, but they're not actively living in any conventional sense. Others exist in such extreme conditions that their biochemistry operates by completely different rules than the life we're familiar with. Some thermophiles, for example, have proteins that would be completely denatured and non-functional at normal temperatures. Their entire biochemical machinery is adapted to work only in extreme heat. These discoveries have led to the development of new frameworks for thinking about life, such as the concept of weird life, hypothetical organisms that might use biochemistry so different from terrestrial life that we might not recognize them as living even if we encountered them. For example, could there be organisms that use liquid ammonia instead of water as their primary solvent? Water has many properties that make it ideal for life as we know it, but ammonia also has some advantages. It remains liquid at much lower temperatures than water, which might allow life to exist on very cold worlds. Could there be silicon-based life forms that use silicon instead of carbon as their primary structural element? Silicon can form many of the same types of chemical bonds as carbon, though it's generally less versatile. But in environments where carbon is scarce and silicon is abundant, silicon-based biochemistry might be favored. Could there be organisms that exist as patterns of information rather than physical structures? Some scientists have speculated about digital life, self-replicating patterns of information that could exist in computer networks or even in the quantum vacuum itself. These ideas might sound like science fiction, but they're based on serious scientific reasoning. If life is truly a universal phenomenon, then it might exist in forms that are completely alien to our experience. Understanding the principles that govern life in extreme environments on Earth might help us recognize and understand these alien forms of life if we encounter them. The study of extremophiles has also led to practical applications that benefit humanity. Many of the enzymes produced by extremophiles are valuable for industrial processes. Heat-stable enzymes from thermophiles are used in manufacturing processes that require high temperatures. Acid-resistant enzymes from acidophiles are used in biotechnology applications. Cold-adapted enzymes from psychrophiles are used in processes that require low temperatures. Some extremophiles produce compounds that have potential medical applications. Antibiotics from deep-sea bacteria might be effective against drug-resistant pathogens. Antioxidants from radiation-resistant organisms might help protect against cancer and aging. Antifreeze proteins from psychrophiles might have applications in organ preservation and cryonics. The study of extremophiles is also helping us develop new technologies for extreme environments. Understanding how organisms survive in space conditions is informing the design of life support systems for long-duration space missions. Learning how organisms cope with radiation is helping develop better protection for astronauts and equipment. Perhaps most importantly, extremophiles are teaching us humility about the nature of life. Every time scientists think they've found the absolute limits of life's tolerance, new discoveries push those boundaries even further. Life consistently surprises us with its ability to survive and thrive in conditions that seem impossible. This has profound implications for the search for alien life. If life on Earth can exist in such a wide range of extreme conditions, then the number of potentially habitable environments in the universe is far larger than we ever imagined. Almost any world with liquid water, chemical energy sources, and organic compounds might potentially support some form of life. And as we develop more sophisticated instruments and techniques for studying extreme environments, we're discovering that life is even more widespread on Earth than we thought. Every new extreme environment that scientists explore seems to harbor its own unique community of organisms. The deep subsurface biosphere extends far deeper than anyone expected. Organisms have been found living in ice, in rock, in highly saline lakes, in radioactive waste sites, and in environments that were thought to be completely sterile. Life, it seems, will find a way to survive almost anywhere that liquid water can exist and energy is available. This ubiquity of life in extreme environments gives us reason for optimism in our search for alien life. If life is so tenacious and adaptable on Earth, then it might be equally tenacious and adaptable elsewhere in the universe. The cosmos might be far more alive than we ever dared to hope. But extremophiles also remind us that alien life might be very different from what we expect. If we encounter life on other worlds, it might be based on completely different biochemistry, might survive in conditions that would be lethal to terrestrial organisms, and might exhibit characteristics that challenge our very definition of what it means to be alive. As we continue to explore the extreme environments of Earth and to search for life on other worlds, we carry with us the lessons learned from extremophiles. They've taught us that life is incredibly creative, remarkably resilient, and endlessly surprising. They've expanded our understanding of what's possible and given us new hope that we might not be alone in the universe. The next time you see a hot spring, a salt lake, or a frozen landscape, remember that these seemingly hostile environments might be teeming with life forms that have evolved remarkable strategies for survival. And remember that similar environments on Mars, Europa, Enceladus, and countless other worlds might also harbor their own unique forms of alien life. The extremophiles of Earth are our best guides to understanding what alien life might look like and where it might be found. They're showing us that the universe might be a far more living place than we ever imagined. Imagine standing on a world where the horizon stretches endlessly in every direction, broken only by towering ridges of ice that rise like frozen mountain ranges from a surface as smooth as polished marble. Above you, the sky is black as velvet, pierced by the pale disk of the sun and the massive looming presence of Jupiter, hanging in the heavens like a swirled giant. Beneath your feet lies something extraordinary, one of the largest oceans in the solar system, hidden beneath miles of solid ice. This is Europa, Jupiter's fourth largest moon, and it represents one of the most promising places to search for alien life in our cosmic neighborhood. For decades, scientists have suspected that this small, icy world harbors a subsurface ocean, but recent evidence has confirmed not only that this ocean exists, but that it contains more than twice as much water as all of Earth's oceans combined. The story of how we discovered Europa's hidden ocean reads like a detective novel, full of subtle clues, brilliant deductions, and surprising revelations. It began in the 1970s when the Voyager spacecraft first flew past Jupiter and its moons, sending back images that puzzled and intrigued scientists. Europa's surface appeared to be covered in a complex network of dark lines crisscrossing the icy terrain like a vast spiderweb. These features, called lineae, looked unlike anything scientists had seen before. Some appeared to be ridges rising above the surrounding terrain, while others looked like valleys or cracks in the ice. The surface was remarkably smooth, with very few impact craters, suggesting that it was geologically young and actively being resurfaced. But the real breakthrough came in the 1990s when NASA's Galileo spacecraft began orbiting Jupiter and studying its moons in unprecedented detail. Galileo's observations revealed that Europa's magnetic field was variable and induced by Jupiter's own powerful magnetic field, exactly what would be expected if a conducting fluid, like salt water, existed beneath the moon's surface. The gravitational data collected by Galileo told an even more compelling story. By carefully tracking the spacecraft's trajectory as it flew past Europa, scientists could map the moon's internal structure. What they found was consistent with a differentiated interior, a metallic core, a rocky mantle, and a water ice shell about 100 kilometers thick. But the most exciting evidence came from detailed analysis of the surface features. The dark lineae that had puzzled scientists since the Voyager era began to make sense when viewed as evidence of a dynamic, active ocean beneath the ice. These features appear to be formed by tidal flexing, the constant stretching and squeezing of Europa's ice shell as the moon orbits Jupiter. Jupiter's enormous gravitational pull creates tides in Europa's subsurface ocean that are thousands of times stronger than the tides we experience on Earth. As Europa follows its slightly elliptical orbit, the strength of these tidal forces varies, causing the ocean to slosh back and forth and the ice shell above to crack, break, and reform. The lineae represent the surface expression of this internal activity. When the ice cracks, darker material from below can seep upward, creating the dark lines that crisscross Europa's surface. Some of these features show evidence of spreading, where the ice has been pulled apart and new material has filled the gap, much like the mid-ocean ridges on Earth, where new seafloor is created. Even more intriguingly, some areas of Europa's surface show evidence of chaos terrain, regions where the original ice has been broken up, rotated, and refrozen in a jumbled pattern. These areas suggest that the ice shell might be relatively thin in some places, allowing the underlying ocean to interact more directly with the surface. But perhaps the most exciting discovery came in 2013, when the Hubble Space Telescope detected what appeared to be water vapor plumes erupting from Europa's south polar region. These plumes, reaching heights of over 200 kilometers above the surface, provided the first direct evidence that Europa's subsurface ocean might sometimes interact directly with space. The detection of these plumes was revolutionary because it suggested that scientists might be able to study Europa's ocean without having to drill through miles of ice. If the plumes contain material from the subsurface ocean, then spacecraft could fly through them and analyze their composition directly, much like how the Cassini mission sampled the plumes of Saturn's moon Enceladus. Follow-up observations have been challenging, with some studies confirming the presence of plumes while others have failed to detect them. This variability suggests that the plumes might be intermittent, perhaps related to Europa's orbital position and the varying strength of tidal forces. But Europa isn't the only moon in our solar system hiding a vast ocean. As our understanding of these hidden seas has grown, we've realized that subsurface oceans might be one of the most common environments in the solar system and possibly the universe. Saturn's moon, Enceladus, despite being much smaller than Europa, has provided some of the most dramatic evidence for an active subsurface ocean. In 2005, the Cassini spacecraft made a startling discovery when it detected water vapor and ice particles streaming from the moon's south polar region. The south pole of Enceladus is marked by 4 parallel fractures dubbed the tiger stripes, from which massive geysers of water vapor and ice particles erupt with tremendous force. These plumes contain not just water, but also organic compounds, nitrogen, and other chemicals that could be the building blocks of life. Cassini's multiple flybys of Enceladus allowed scientists to fly directly through these plumes and analyze their composition in real time. What they found was remarkable. The plumes contain complex organic molecules, including some that are considered precursors to life. The spacecraft also detected hydrogen gas, which on Earth is often associated with hydrothermal vents and the ecosystems that surround them. The presence of hydrogen is particularly significant because it suggests that there might be active chemistry occurring in Enceladus's subsurface ocean. On Earth, hydrogen is produced by hydrothermal vents, where hot water interacts with rock on the ocean floor. If similar processes are occurring in Enceladus's ocean, they could provide the chemical energy needed to support life. Gravitational measurements by Cassini confirmed that Enceladus has a global subsurface ocean beneath its icy shell. This ocean appears to be in direct contact with the Moon's rocky core, which would allow for the kind of water-rock interactions that could produce the chemicals necessary for life. The tidal heating that keeps Enceladus's ocean liquid is similar to what occurs on Europa, but with some important differences. Saturn's gravitational pull, combined with the gravitational influences of other moons in the Saturn system, creates complex tidal forces that not only keep the ocean liquid, but also drive the geological activity that powers the geysers. The fact that Enceladus is actively venting material from its subsurface ocean makes it one of the most accessible alien environments in the solar system. Unlike Europa, where we would need to drill through miles of ice to reach the ocean, Enceladus is literally spraying samples of its hidden sea into space for us to collect and analyze. But perhaps the strangest and most alien ocean world in our solar system is Titan, Saturn's largest moon. Titan is unique among solar system bodies because it's the only moon with a substantial atmosphere, thicker than Earth's, and the only world besides Earth known to have stable liquid on its surface. But Titan's surface liquids aren't water. They're hydrocarbons, methane and ethane that exist as liquids in Titan's frigid environment. The surface temperature on Titan is about 290 degrees Fahrenheit, far too cold for liquid water to exist on the surface. Titan's landscape, revealed by the Cassini mission and the Huygens probe that landed on the surface in 2005, looks remarkably Earth-like in some ways. There are rivers, lakes and seas, all filled with liquid methane and ethane. There are sand dunes made of hydrocarbon particles. There are clouds and weather patterns driven by the evaporation and condensation of methane. But beneath this alien surface lies something even more remarkable, a subsurface ocean of liquid water. Radar observations from Cassini revealed that Titan, like Europa and Enceladus, has a layer of liquid water beneath its icy crust. This ocean might be even larger than Europa's, potentially containing several times more water than all of Earth's oceans. The presence of both surface hydrocarbons and a subsurface water ocean makes Titan unique in the solar system. It's essentially two different worlds stacked on top of each other, a hydrocarbon world at the surface and a water world beneath. This dual nature raises fascinating questions about the potential for life on Titan. Could there be organisms in the subsurface water ocean similar to what we might find on Europa or Enceladus? And could there be completely different forms of life in the hydrocarbon lakes and seas on the surface, organisms that use liquid methane instead of water as their biological solvent? The possibility of methane-based life on Titan's surface might sound like science fiction, but it's being seriously considered by astrobiologists. Laboratory experiments have shown that complex organic chemistry can occur in liquid methane environments, and some researchers have proposed specific biochemical pathways that could support life in Titan's hydrocarbon seas. Such life would be radically different from anything on Earth. It would need to operate at extremely low temperatures and use completely different chemical processes. But the basic principles of life, the ability to process information, reproduce and evolve, might still apply. The diversity of ocean worlds in our solar system extends beyond the famous moons of Jupiter and Saturn. Ganymede, Jupiter's largest moon, also appears to harbour a subsurface ocean. Callisto, another of Jupiter's large moons, might have a subsurface ocean as well, though the evidence is less certain. Even more intriguingly, several moons in the outer solar system might contain hidden oceans. Triton, Neptune's largest moon, shows evidence of geological activity that might be driven by tidal heating and a subsurface ocean. Some of the larger moons of Uranus might also harbour subsurface seas. The discovery of so many potential ocean worlds has revolutionized our understanding of habitability in the solar system. Before we knew about these hidden seas, scientists focused primarily on the traditional habitable zone around stars, the region where liquid water could exist on planetary surfaces. But subsurface oceans exist far outside the traditional habitable zone, kept liquid by tidal heating rather than stellar energy. This means that potentially habitable environments might exist around virtually any star, regardless of the distance of planets or moons from their host star. The implications for astrobiology are profound. If subsurface oceans are common in our solar system, and by extension, in planetary systems throughout the galaxy, then the number of potentially habitable environments in the universe might be far larger than we ever imagined. But subsurface oceans also present unique challenges for the search for life. Unlike surface environments, which can be studied remotely using telescopes, subsurface oceans are hidden beneath miles of ice and rock. Detecting and studying potential life in these environments requires sophisticated instruments and innovative techniques. One of the most promising approaches is to study the composition of materials that escape from these subsurface oceans. The plumes of Europa and Enceladus provide direct samples of subsurface ocean material that can be analyzed by spacecraft flying through them. Future missions are being designed specifically to take advantage of these opportunities. NASA's Europa Clipper mission, scheduled to launch in the 2020s, will make multiple flybys of Europa, studying its ice shell, mapping its subsurface ocean, and analyzing any plumes that might be active during the mission. The European Space Agency's JUICE mission, Jupiter, Icy Moons Explorer, will study Jupiter's icy moons including Europa, Ganymede and Callisto, with particular focus on their subsurface oceans and potential habitability. Even more ambitious missions are being planned that would actually land on these icy worlds and attempt to reach their subsurface oceans. Concepts include ice-penetrating probes that could melt their way through the ice shells, autonomous underwater vehicles that could explore the oceans beneath, and sample return missions that could bring ocean material back to Earth for detailed analysis. One of the most exciting possibilities is the potential for discovering not just evidence of life, but living organisms themselves. Unlike the search for ancient life on Mars, which focuses on fossils and chemical traces left behind by organisms that might have lived billions of years ago, the search for life in subsurface oceans could potentially find organisms that are alive today. Imagine the moment when a robotic submarine first deploys in Europa's subsurface ocean and its cameras reveal strange, alien organisms swimming in the darkness. Or picture the excitement when chemical analysis of Enceladus's plumes reveals complex organic molecules that can only be produced by biological processes. These scenarios might not be as far-fetched as they sound. The subsurface oceans of icy moons have several characteristics that make them potentially very good habitats for life. They're protected from radiation by miles of ice above them. They're stable over geological timescales, providing billions of years for life to evolve. And they contain the basic ingredients that life needs: liquid water, organic compounds, and energy sources. The energy sources in these environments come primarily from chemical processes rather than sunlight. Tidal heating drives geological activity that can create hydrothermal vents on the ocean floors. The interaction between liquid water and rocky surfaces can produce hydrogen and other chemicals that could serve as food for primitive organisms. On Earth, we know that life can thrive in similar environments. Deep-sea hydrothermal vents host thriving ecosystems that depend on chemical energy rather than sunlight. These communities include bacteria, archaea, and more complex organisms like tube worms, shrimp, and fish. If similar ecosystems exist in the subsurface oceans of icy moons, they might be home to organisms that are completely independent of surface conditions. Such life would be truly alien, organisms that have evolved in perpetual darkness under crushing pressure in an environment that has never known the warmth of a star. But the search for life in subsurface oceans isn't just about finding alien organisms. It's also about understanding the fundamental principles of biology and the conditions that allow life to emerge and thrive. If we discover that life exists in multiple subsurface oceans in our solar system, it would suggest that life is a common and perhaps inevitable consequence of the right chemical and physical conditions. It would mean that the universe might be teeming with life, hidden beneath the surfaces of countless icy worlds orbiting stars throughout the galaxy. On the other hand, if we thoroughly explore these subsurface oceans and find them to be sterile, it would tell us something important about the rarity and fragility of life. It might suggest that the emergence of life requires more specific conditions than we currently understand. Either result would be scientifically revolutionary, the discovery of alien life would be one of the most important discoveries in human history, fundamentally changing our understanding of biology and our place in the universe. But even the failure to find life would advance our understanding of what makes life possible and how rare it might be. The exploration of subsurface oceans also has implications for the future of human space exploration. These vast bodies of liquid water could potentially serve as resources for future space missions, providing water for drinking, oxygen for breathing, and hydrogen for fuel. The icy moons of the outer solar system might become important waypoints for future human exploration of the outer solar system. Bases on Europa or Enceladus could serve as staging areas for missions to the outer planets and beyond, taking advantage of the abundant water resources available beneath the ice. But perhaps the most profound implication of discovering subsurface oceans is what it tells us about the prevalence of habitable environments in the universe. If icy moons with subsurface oceans are common in our solar system, they're probably common throughout the galaxy as well. Current estimates suggest that there might be more water in the subsurface oceans of icy moons than in all the surface oceans of all the planets combined. If that's true, then the majority of liquid water in the universe, and potentially the majority of life, might exist in subsurface environments rather than on planetary surfaces. This realization has led to a fundamental shift in how astrobiologists think about habitability. Instead of focusing exclusively on planets in the habitable zones of stars, scientists are now considering the possibility that the most common habitable environments in the universe might be subsurface oceans on moons and small planets. These environments would be largely independent of stellar conditions, depending instead on internal heat sources like tidal heating and radioactive decay. This means that habitable environments could exist around virtually any type of star and could remain habitable for billions of years regardless of changes in stellar output. The study of subsurface oceans in our solar system is still in its early stages, but already it has revolutionized our understanding of where life might exist in the universe. As we continue to explore these hidden seas with increasingly sophisticated instruments and techniques, we may discover that we live in a galaxy where life is far more common than we ever dared to hope. The next few decades promise to be an exciting time for the exploration of subsurface oceans. Multiple missions are planned or under development that will study these environments in unprecedented detail. New technologies are being developed that will allow us to penetrate the ice shells and explore the oceans beneath. And as our understanding of these environments grows, we're developing new strategies for searching for life that take advantage of the unique characteristics of subsurface oceans. These strategies include studying the chemistry of plume materials, looking for seasonal or orbital variations that might indicate biological activity, and developing instruments that can detect the subtle signatures of life in the darkness beneath the ice. The hidden oceans of our solar system represent some of the most promising places to search for alien life. They're accessible with current or near-future technology. They contain environments that we know can support life, and they might preserve evidence of biological activity for billions of years. As we stand on the threshold of exploring these alien seas, we can't help but wonder what we might find in their dark depths. Will we discover thriving ecosystems adapted to life in perpetual darkness? Will we find evidence of ancient life preserved in the ice above? Or will we find something completely unexpected, forms of life so alien that they challenge our very understanding of what it means to be alive? Whatever we discover, the exploration of subsurface oceans will undoubtedly be one of the most important scientific endeavors of the 21st century. These hidden seas might hold the key to answering one of humanity's oldest questions: are we alone in the universe? The answer to that question might be swimming in the dark waters beneath the ice of Europa, jetting through the geysers of Enceladus, or floating in the methane seas of Titan. And we might not have to wait much longer to find out. On October 6, 1995, two Swiss astronomers made an announcement that would forever change our understanding of our place in the universe. Michel Maire and Didier Queloz, working at the Haute-Provence Observatory in France, declared that they had discovered the first planet orbiting a sun-like star beyond our solar system. The planet, designated 51 Pegasi b, was nothing like anything in our cosmic neighborhood. This alien world was a gas giant roughly half the mass of Jupiter, but it orbited its star every 42 days at a distance closer than Mercury orbits our Sun. The surface temperature was estimated to be over 1,800 degrees Fahrenheit, hot enough to melt iron. It was a hellish world that challenged everything astronomers thought they knew about how planetary systems form and evolve. But 51 Pegasi b was just the beginning. In the nearly 3 decades since that historic discovery, we've identified over 5,000 confirmed exoplanets, with thousands more candidates awaiting confirmation. Each new discovery has revealed that the universe contains a stunning diversity of worlds, many unlike anything in our solar system. The story of exoplanet detection is really a story of human ingenuity and technological advancement. Detecting planets around other stars is extraordinarily difficult because planets are much smaller and dimmer than the stars they orbit. A typical planet reflects or emits only about a billionth as much light as its host star, making direct detection nearly impossible with current technology. The breakthrough that led to the discovery of 51 Pegasi b was the radial velocity method, also known as the Doppler method. This technique doesn't detect planets directly, but instead looks for the tiny gravitational wobble that a planet induces in its host star as it orbits. When a planet orbits a star, both objects actually orbit around their common center of mass, called the barycenter. For a system like Jupiter and the Sun, this barycenter lies just outside the Sun's surface, causing the Sun to wobble slightly as Jupiter completes its 12-year orbit. This wobble causes periodic shifts in the star's spectrum due to the Doppler effect, the same phenomenon that causes an ambulance siren to change pitch as it passes by. By carefully measuring these spectral shifts, astronomers can determine the presence of a planet, estimate its mass, and characterize its orbit. The precision required is extraordinary. Detecting an Earth-mass planet around a Sun-like star requires measuring velocity changes of about 9 centimeters per second, roughly the speed of a walking person. The early discoverers using the radial velocity method revealed a surprising population of hot Jupiters, gas giant planets orbiting very close to their stars. These worlds challenged the prevailing theories of planetary formation, which suggested that gas giants should form far from their stars where temperatures are cold enough for ice to condense. The existence of hot Jupiters led to the development of new theories involving planetary migration. Scientists now believe that many planets form in one location and then migrate inward or outward due to gravitational interactions with other planets or with the disk of gas and dust from which they formed. But the real revolution in exoplanet science came with the development of the transit method. This technique detects planets by looking for the tiny dimming that occurs when a planet passes in front of its star as seen from Earth. The amount of dimming depends on the size of the planet relative to its star, an Earth-sized planet crossing a sun. Like star causes a dimming of only 0.08%. The transit method has several advantages over radial velocity observations. It can detect smaller planets, including potentially habitable Earth-sized worlds. It provides information about the planet's size and orbital period. And when combined with radial velocity measurements, it can determine the planet's density and composition. The Kepler Space Telescope, launched by NASA in 2009, was specifically designed to search for transiting exoplanets. Over its 4-year primary mission, Kepler stared at a single patch of sky containing about 150,000 stars, monitoring their brightness with unprecedented precision. Kepler's discoveries revolutionized our understanding of planetary systems. The mission found that small planets are much more common than large ones, that multi-planet systems are typical rather than exceptional, and that there's a whole population of planets between the size of Earth and Neptune that don't exist in our solar system. One of Kepler's most important discoveries was the prevalence of super-Earths, planets larger than Earth but smaller than Neptune. These worlds, with masses between 1 and 10 times that of Earth, appear to be the most common type of planet in the galaxy. Yet our solar system contains no examples of super-Earths, suggesting that our planetary system might be unusual in this respect. Kepler also discovered remarkable planetary systems that challenged our understanding of orbital dynamics. The TRAPPIST-1 system, for example, contains 7 Earth-sized planets orbiting a small dim red dwarf star. 3 of these planets orbit in the star's habitable zone, where liquid water could potentially exist on their surfaces. Even more exotic are planets with highly elliptical orbits, planets orbiting binary stars, and planets that orbit their stars in retrograde direction. One system, Kepler-16, contains a planet that orbits both stars in a binary system, a real-life version of the fictional planet Tatooine from Star Wars. The diversity of exoplanetary systems has forced astronomers to reconsider many of their assumptions about planetary formation and evolution. It appears that our solar system, with its orderly arrangement of small rocky planets close to the Sun and giant gas planets farther out, might be relatively unusual. But perhaps the most exciting aspect of exoplanet research is the growing ability to study the atmospheres of these distant worlds. When a planet transits its star, some of the star's light passes through the planet's atmosphere before reaching Earth. By analyzing this light with spectroscopy, astronomers can determine the chemical composition of alien skies. The first atmospheric detections were made for hot Jupiter planets whose extended atmospheres are easier to study. These observations revealed the presence of water vapor, methane, carbon monoxide, and other molecules in the atmospheres of gas giant exoplanets. More recently, astronomers have begun to study the atmospheres of smaller, potentially rocky planets. In 2022, the James Webb Space Telescope obtained the first spectrum of a rocky exoplanet's atmosphere, revealing that the planet, WASP, has water vapor and clouds in its atmosphere. The ability to study exoplanet atmospheres opens up the possibility of detecting biosignatures, chemical evidence of life. On Earth, life has fundamentally altered our planet's atmosphere. The 21% oxygen concentration in our atmosphere is maintained by photosynthetic organisms and would quickly disappear if life ceased to exist. Other potential biosignatures include the simultaneous presence of oxygen and methane, which react with each other and would disappear unless continuously replenished. Seasonal variations in atmospheric composition that might indicate biological cycles, and industrial pollutants that could only be produced by technological civilizations. The search for biosignatures has focused particularly on planets in the habitable zone, or Goldilocks zone, the region around a star where temperatures are suitable for liquid water to exist on a planet's surface. The location of this zone depends on the star's temperature and luminosity. For our Sun, the habitable zone extends roughly from Venus's orbit to Mars's orbit. Kepler discovered numerous planets in the habitable zones of their stars, including some that are remarkably similar to Earth in size and orbital characteristics. Kepler 450b, dubbed Earth's cousin, is about 60% larger than Earth and orbits a Sun-like star in the habitable zone with a year lasting 385 days. However, being in the habitable zone doesn't guarantee that a planet is actually habitable. Venus is technically in our Sun's habitable zone, but its thick carbon dioxide atmosphere creates a runaway greenhouse effect that makes its surface temperature hot enough to melt lead. Many factors affect a planet's habitability beyond its distance from its star. The composition and thickness of its atmosphere, the strength of its magnetic field, the tilt of its rotation axis, the eccentricity of its orbit, and the activity level of its host star all play important roles in determining whether a world can support liquid water and potentially life. Red dwarf stars, which make up about 75% of all stars in the galaxy, present particular challenges for habitability. These small, dim stars have habitable zones that are very close to the star, meaning that planets in the habitable zone are likely to be tidally locked, with one side permanently facing the star and the other side permanently dark. Tidally locked planets experience extreme temperature differences between their day and night sides, which could prevent the existence of liquid water. However, recent climate models suggest that thick atmospheres might be able to redistribute heat from the day side to the night side, potentially making these worlds habitable despite their extreme conditions. Red dwarf stars are also much more active than Sun-like stars, producing frequent flares that bombard nearby planets with harmful radiation. However, red dwarfs have much longer lifespans than larger stars, potentially giving life billions of years longer to evolve and develop. The study of exoplanet habitability has led to the concept of the habitable zone around the habitable zone, the idea that there might be optimal distances from different types of stars where conditions are most favorable for life. This expanded view of habitability considers not just temperature, but also stellar radiation, atmospheric dynamics, and planetary magnetic fields. One of the most exciting recent developments in exoplanet science is the detection of potentially habitable planets around the nearest stars to our solar system. Proxima Centauri, B, orbiting the closest star to our Sun at a distance of just 4.2 light-years, is roughly Earth-sized and orbits in its star's habitable zone. While Proxima Centauri is a red dwarf star with the associated challenges for habitability, the proximity of Proxima b makes it an ideal target for detailed study. Several ambitious projects, including Breakthrough Starshot, propose sending tiny spacecraft to the Proxima Centauri system to study the planet up close. Another nearby potentially habitable world is Gliese 667cc, which orbits a red dwarf star about 22 light-years from Earth. This super-Earth has a mass about 4.5 times that of Earth and receives slightly more energy from its star than Earth receives from the Sun. The detection of these nearby, potentially habitable worlds has sparked serious discussions about interstellar exploration. While the distances involved are vast by human standards, they're not insurmountable with sufficiently advanced technology. A spacecraft traveling at 10% the speed of light could reach Proxima Centauri in about 40 years. But we don't need to wait for interstellar travel to study these worlds in detail. The next generation of space telescopes will be capable of directly imaging Earth-sized exoplanets and studying their atmospheres for signs of habitability and potentially even life. The James Webb Space Telescope, which began operations in 2022, represents a major step forward in exoplanet characterization. Its large mirror and sensitive instruments can study the atmospheres of smaller planets than was previously possible, and its infrared sensitivity allows it to detect heat from planets themselves rather than just reflected starlight. Future missions will push these capabilities even further. The proposed HABEX, Habitable Exoplanet Observatory, and LUVOIR, Large Ultraviolet Optical Infrared Surveyor, telescopes would be capable of directly imaging Earth-sized planets in the habitable zones of nearby stars and studying their atmospheres for biosignatures. These next-generation telescopes will use advanced techniques like coronagraphy to block out the light from host stars and reveal the much dimmer light from orbiting planets. This is an extraordinarily challenging technical feat, like trying to see a firefly next to a searchlight from thousands of miles away. But the potential scientific payoff is enormous. Direct imaging of exoplanets would allow astronomers to study their atmospheric composition, weather patterns, and surface properties in unprecedented detail. It might even be possible to detect seasonal changes that could indicate the presence of vegetation or other signs of life. The diversity of exoplanets discovered so far suggests that the universe contains an almost infinite variety of worlds. There are planets made of diamond, worlds where it rains liquid metal, and planets so close to their stars that they're completely molten on one side. There are planets orbiting dead stars, planets floating freely through space without any star at all, and planets in systems with multiple stars. One of the most bizarre classes of exoplanets are the puffy planets, gas giants with such low densities that they would float in water if you could find an ocean large enough. These planets have been heated and inflated by their proximity to their host stars, creating worlds with the mass of Jupiter but the size of a much larger planet. At the other extreme are the supermercuries, small, dense planets that orbit extremely close to their stars. These worlds are likely composed mostly of iron and other heavy elements, with their lighter materials stripped away by intense stellar radiation. Some planets experience such extreme tidal forces that they're being slowly destroyed by their host stars. These evaporating planets leave comet-like tails of material streaming behind them as they orbit, gradually losing mass until they may eventually disappear entirely. Perhaps most intriguingly, some exoplanets might be ocean worlds, planets whose surfaces are entirely covered by deep oceans. These worlds could potentially harbor life in their global seas, protected from space radiation by their deep water layers. The study of exoplanet composition has revealed surprising diversity in planetary materials. While Earth is made primarily of rock and metal, many exoplanets appear to be water worlds with significant amounts of water ice or liquid water. Others might be carbon planets with surfaces made of diamond or graphite rather than the silicate rocks we're familiar with. The atmospheric compositions of exoplanets are equally diverse. Hot Jupiters often have atmospheres dominated by hydrogen and helium, but they can also contain significant amounts of water vapor, methane, carbon monoxide, and even exotic compounds like titanium oxide that condense into clouds at high temperatures. Some exoplanets have atmospheres so hot that their atmospheric metals exist in gaseous form, creating clouds of vaporized iron and other elements. These worlds experience weather patterns unlike anything on Earth, with metal rain and hurricane-force winds driven by extreme temperature differences. The detection of weather patterns on exoplanets has become an active area of research. Using sophisticated observing techniques, astronomers can map temperature variations across the surfaces of tidally locked planets, track the movement of atmospheric features, and even detect the formation and dissipation of clouds. One particularly interesting phenomenon is atmospheric escape, the process by which planets lose their atmospheres to space. This is especially important for planets orbiting close to active stars, where intense stellar radiation can strip away atmospheric components over time. Some planets show evidence of having lost substantial portions of their original atmospheres, while others appear to be actively losing atmosphere today. Understanding atmospheric escape is crucial for determining the long-term habitability of exoplanets, especially those orbiting red dwarf stars. The search for biosignatures in exoplanet atmospheres is still in its early stages, but several promising candidates have been identified. The detection of water vapor in the atmospheres of several potentially habitable exoplanets has raised excitement about their potential to support life. One particularly intriguing world is K2-18b, a sub-Neptune exoplanet about 110 light-years from Earth. This planet orbits in its star's habitable zone and has been found to have water vapor in its atmosphere along with hydrogen and helium. While K2-18b is likely too massive to be truly Earth-like, it demonstrates that water can exist in the atmospheres of planets outside our solar system. The recent detection of possible biosignature gases in some exoplanet atmospheres has generated considerable excitement and debate. Phosphine, a gas that on Earth is almost exclusively produced by living organisms, has been tentatively detected in the atmosphere of Venus and possibly in some exoplanet atmospheres. However, the interpretation of these detections remains controversial. Natural processes can sometimes produce molecules that we think of as biosignatures, and distinguishing between biological and non-biological origins requires careful analysis and multiple lines of evidence. This has led to the development of more sophisticated frameworks for evaluating potential biosignatures. Rather than relying on single molecules, scientists are looking for combinations of gases that would be difficult to produce through non-biological processes, or for patterns of atmospheric composition that might indicate biological activity. The search for technosignatures, evidence of technological civilizations, in exoplanet atmospheres represents an even more speculative but potentially revolutionary area of research. Industrial pollutants like chlorofluorocarbons, CFCs, would be clear evidence of technological activity if detected in an exoplanet atmosphere. Artificial lights on the night side of tidally locked planets could potentially be detected by future telescopes. Large-scale engineering projects like solar collectors or atmospheric processors might create distinctive signatures in a planet's spectrum or thermal emission. While these technosignatures would be extremely difficult to detect with current technology, they represent an important complement to the search for simple biosignatures. The detection of either would represent one of the most important discoveries in human history. The study of exoplanets has also provided new insights into the formation and evolution of planetary systems. The discovery of planetary migration, where planets move from their original formation locations, has helped explain the diversity of exoplanetary systems. Hot Jupiters, for example, likely formed in the outer regions of their planetary systems and then migrated inward due to interactions with the gas disk from which they formed. This migration can disrupt the formation of terrestrial planets in the inner system, potentially explaining why some planetary systems lack Earth-like worlds. The timing and extent of planetary migration appears to be a crucial factor in determining whether a planetary system can host potentially habitable worlds. Systems where migration occurred early or was extensive might have cleared out their habitable zones, while systems with more limited migration might preserve conditions suitable for the formation and survival of Earth-like planets. The discovery of compact planetary systems, where multiple planets orbit very close to their host stars, has challenged our understanding of planetary formation. Some systems contain more planets packed into the orbit of Mercury than our entire solar system contains total. These compact systems appear to form through a different process than systems like ours, possibly involving the early inward migration of planetary building blocks. Understanding why some systems develop compact architectures while others develop more spread out configurations, like our solar system, is an active area of research. The study of planetary system architectures has implications for habitability that go beyond individual planets. The presence of giant planets in a system can affect the delivery of water and organic compounds to terrestrial planets through their gravitational influence on asteroids and comets. Jupiter's role in our solar system as both a cosmic vacuum cleaner that removes potentially hazardous asteroids and comets, and as a gravitational shepherd that directs water-rich bodies toward the inner planets, might be crucial for Earth's habitability. Understanding whether other planetary systems have similar protective mechanisms is important for assessing their potential to host life. The detection of exoplanets has also revealed the importance of stellar properties for planetary habitability. Stars of different masses and ages create different environments for their planetary systems, affecting everything from atmospheric retention to the delivery of energy for potential biological processes. The most massive stars burn through their fuel quickly and end their lives in violent supernova explosions that would sterilize nearby planets. The least massive stars live for trillions of years, but produce little energy and subject close-in planets to intense flares and radiation. The intermediate mass stars, like our Sun, appear to provide the most stable and long-lived environments for planetary habitability. However, the small red dwarf stars, despite their challenges, might be the most important for astrobiology simply because they're so numerous and long-lived. The field of exoplanet science continues to evolve rapidly as new detection methods are developed and new telescopes come online. Ground-based surveys like the Transiting Exoplanet Survey Satellite, CESS, are discovering thousands of new planetary candidates, while sophisticated radial velocity surveys are characterizing their masses and compositions. Future space missions will push the boundaries of what's possible in exoplanet detection and characterization. The European Space Agency's PLA TOW mission will search for Earth-like planets around Sun-like stars, while NASA's Roman Space Telescope will use gravitational microlensing to detect planets throughout the galaxy. The ultimate goal of exoplanet science is to answer the question of whether Earth-like worlds are common in the universe and whether any of them show signs of life. We're closer to answering these fundamental questions than ever before, and the next decade promises to bring revolutionary discoveries. As we continue to discover and study exoplanets, we're building a comprehensive picture of the diversity of worlds in the universe. Each new discovery adds to our understanding of planetary formation, evolution, and habitability, bringing us closer to answering whether we're alone in the cosmos. The thousands of exoplanets discovered so far represent just a tiny fraction of the hundreds of billions of planets that likely exist in our galaxy alone. As our detection methods improve and our surveys become more comprehensive, we'll undoubtedly discover even more exotic and potentially habitable worlds. The study of exoplanets has already shown us that the universe is far stranger and more wonderful than we ever imagined. And we're just getting started in our exploration of these distant worlds. The next chapter in exoplanet science promises to be the most exciting yet, as we begin to study the atmospheres of potentially habitable worlds in detail and search for the first signs of life beyond our solar system. At 10:06 p.m. on September 15, 1977, something extraordinary happened at Stanford University's Big Ear Radio Observatory in Ohio. The facility's computer, methodically scanning the sky for any unusual radio emissions, detected a signal so powerful and precisely tuned that it seemed to leap out of the cosmic background noise like a beacon in the darkness. The signal lasted exactly 72 seconds, the maximum time the telescope could observe any point in the sky, as Earth's rotation carried it across the receiver's field of view. When astronomer Jerry Emmon arrived at the observatory the next morning and reviewed the previous night's data, he was so stunned by what he saw that he grabbed a red pen and wrote, "Wow!" in the margin of the computer printout. That exclamation would become one of the most famous annotations in the history of science, marking what remains the most promising candidate for an extraterrestrial signal ever detected. The "wow" signal came from the direction of the constellation Sagittarius, and its frequency was 1420.4556 MHz, remarkably close to the hydrogen line at 1020.458 MHz. This frequency holds special significance for astronomers because hydrogen is the most abundant element in the universe, and many scientists had theorized that any civilization attempting to communicate across interstellar distances would choose this natural cosmic frequency as an obvious choice for their transmissions. But here's what made the "wow" signal so tantalizing and so frustrating. Despite decades of subsequent observations, including repeated attempts to detect it again with increasingly sophisticated equipment, the signal has never been heard again. Was it a one-time transmission from an alien civilization, a natural phenomenon we don't understand, or something else entirely? The "wow" signal represents both the promise and the challenge of the search for extraterrestrial intelligence, or SETI. For more than 6 decades, scientists have been systematically scanning the skies for any sign that we're not alone in the universe, using radio telescopes to listen for artificial signals that might indicate the presence of technological civilizations among the stars. The modern era of SETI began in 1960, when astronomer Frank Drake conducted the first systematic search for extraterrestrial radio signals. Using the 85-foot radio telescope at the National Radio Astronomy Observatory in Green Bank, West Virginia, Drake pointed his instrument at 2 nearby sun-like stars, Tau Ceti and Epsilon Eridani, and listened for any artificial signals. Drake's project, called Project Ozma after the Queen of the fictional Land of Oz, detected nothing unusual during its 150 hours of observations. But it established the basic methodology that would guide SETI research for decades to come. Use sensitive radio telescopes to monitor nearby star systems for narrow-band signals that couldn't be produced by natural astronomical phenomena. The rationale behind radio SETI is compelling. Radio waves can travel vast distances through space without being significantly absorbed or scattered by interstellar dust and gas. A civilization with technology comparable to our own could produce radio signals powerful enough to be detected across thousands of light years. And any technological civilization would likely discover radio waves early in their development, making it a logical choice for interstellar communication. But as Drake quickly realized, searching for extraterrestrial signals is like looking for a needle in a haystack the size of the universe. The radio spectrum contains millions of possible frequencies where a signal might be transmitted. There are hundreds of billions of stars in our galaxy, each potentially hosting planets that might harbor intelligent life, and we don't know when such signals might be transmitted or how long they might last. To focus their search, SETI scientists have developed strategies based on educated guesses about how extraterrestrial civilizations might communicate. They've focused on waterhole frequencies, the radio frequencies between the hydrogen line at 1420 MHz and the hydroxyl radical lines around 1665 MHz, reasoning that these frequencies might have special significance for any civilization that evolved in a water-rich environment. What? They've searched for signals from star systems that are similar to our own, on the theory that sun-like stars might be most likely to host Earth-like planets with intelligent life. They've looked for signals with characteristics that would clearly indicate artificial origin, narrow bandwidth, precise frequency, or patterns that couldn't be produced by natural processes. Over the decades, SETI searches have become increasingly sophisticated and comprehensive. The SETI Institute, founded in 1984, has coordinated many of the most ambitious searches, including Project Phoenix, which used large radio telescopes around the world to systematically observe nearby sun-like stars. Modern SETI projects can simultaneously monitor millions of frequency channels and observe thousands of star systems at once. They use advanced signal processing techniques to filter out interference from human technology and identify potential artificial signals. Some projects even enlist the help of millions of volunteers through distributed computing programs like SETI Home. The Breakthrough Listen project, launched in 2015 with funding from Russian billionaire Yuri Milner, represents the most comprehensive search for extraterrestrial intelligence ever undertaken. Using some of the world's most powerful radio telescopes, including the 100-meter Green Bank telescope and the 64-meter Parkes telescope, Breakthrough Listen is surveying millions of stars for any sign of artificial radio transmissions. What makes Breakthrough Listen special is its unprecedented scope and sensitivity. The project can detect signals thousands of times weaker than previous searches could find. It's scanning a much broader range of frequencies from 1 to 50 GHz and looking for a wider variety of signal types. It can monitor thousands of stars simultaneously and process vast amounts of data in real time. But radio waves aren't the only way to search for extraterrestrial intelligence. SETI scientists are also looking for optical signals, brief flashes of laser light that might represent attempts at interstellar communication. Optical SET has some advantages over radio. SETI laser pulses can be incredibly bright, potentially outshining their host stars for brief moments, making them detectable across vast distances. The idea behind optical SETI is that an advanced civilization might use powerful lasers to send signals across interstellar space. These signals would appear as brief, intense flashes of light that could be distinguished from natural astronomical phenomena by their short duration and their location, coincident with nearby stars. Several optical SETT projects are currently operating, including searches at Harvard University and the University of California, Berkeley. These projects use sensitive photodetectors to monitor thousands of stars for nanosecond duration laser pulses that might indicate artificial signals. But SETI has evolved beyond just searching for intentional communications. Modern searches also look for techno-signatures, evidence of alien technology that might be detectable even if it wasn't intended to communicate with us. This approach recognizes that any sufficiently advanced technological civilization would inevitably modify its environment in ways that might be observable across interstellar distances. One of the most intriguing techno-signatures is the possibility of detecting Dyson spheres, or Dyson swarms, hypothetical megastructures that an advanced civilization might build around their star to capture its energy output. These structures would absorb the star's visible light and re-emit it as infrared radiation, creating a distinctive signature that might be detectable by infrared telescopes. In 2015, astronomers discovered a star called KIC 8462852, nicknamed Tabby star after astronomer Tabitha Boyajian, that showed unusual dimming patterns that some scientists suggested might be evidence of alien megastructures. The star's brightness decreased by up to 22% over periods of days to weeks in irregular patterns that didn't match any known natural phenomenon. While subsequent observations have suggested that the dimming is more likely caused by clouds of dust or debris around the star, Tabby star highlighted the potential for detecting techno-signatures through careful observation of stellar variability. Several projects now systematically monitor millions of stars for any unusual dimming patterns that might indicate the presence of artificial structures. Another promising techno-signature is the detection of industrial pollution in exoplanet atmospheres. On Earth, our industrial civilization has pumped chlorofluorocarbons, CFCs, nitrogen dioxide, and other artificial compounds into our atmosphere. These molecules don't occur naturally in significant quantities and would be clear evidence of technological activity if detected around another world. Future telescopes might be sensitive enough to detect these industrial signatures in the atmospheres of nearby exoplanets. The James Webb Space Telescope, for example, might be able to detect CFCs in the atmosphere of a planet like Proxima Centauri b if they were present in concentrations similar to those in Earth's atmosphere during the peak of CFC production. Even more ambitious technosignature searches look for evidence of planetary engineering or terraforming. An advanced civilization might modify their planet's atmosphere to make it more suitable for their needs, or they might undertake massive construction projects that would be visible from interstellar distances. Artificial lights on the night side of exoplanets could potentially be detected by future telescopes. A civilization that had developed electric lighting on a global scale might create a detectable signature in the infrared spectrum of their planet. While this would be extremely challenging to detect with current technology, it represents a realistic target for next-generation telescopes. But perhaps the most revolutionary development in the search for extraterrestrial intelligence has been the recent acknowledgement by government agencies that unidentified aerial phenomena. UAPs, formerly known as UFOs, deserve serious scientific investigation. For decades, reports of strange objects in our skies were dismissed by mainstream science and relegated to the realm of conspiracy theories and science fiction. But in recent years, this has begun to change. In 2020, the US Pentagon officially released videos showing objects that appear to perform maneuvers beyond the capabilities of any known human technology. These videos, recorded by military sensors and confirmed by multiple independent sources, show objects that appear to accelerate at rates that would crush any human pilot, make sharp turns that violate our understanding of aerodynamics, and move through air and water with equal ease. The objects show no visible means of propulsion, no jet engines, no rocket exhausts, no rotor blades. In 2021, the Pentagon released a report acknowledging that these phenomena are real and stating that they represent technologies not currently within the US inventory. The report documented 144 instances of UAP encounters by military personnel, noting that most remain unexplained despite extensive investigation. This official acknowledgement has led to a transformation in how the scientific community approaches the UAP phenomenon. NASA has announced that it is beginning a systematic study of UAPs, bringing rigorous scientific methods to bear on these mysterious observations. Universities are establishing research programs dedicated to studying anomalous aerial phenomena. The scientific investigation of UAPs represents a significant shift in approach. Rather than dismissing these reports out of hand, scientists are now applying the same rigorous methods they use to study any other unexplained phenomenon. They're analyzing sensor data, investigating physical evidence, and developing theoretical frameworks to understand what these objects might be. It's important to emphasize that unidentified doesn't mean extraterrestrial. The vast majority of UAP reports likely have conventional explanations: atmospheric phenomena, experimental military technology, instrument malfunctions, or observational errors. But a small percentage of cases remain genuinely puzzling and merit serious scientific investigation. Some UAPs might represent new atmospheric or plasma phenomena that we don't yet understand. Others might be advanced human technology that's more sophisticated than publicly acknowledged. Still others might represent measurement errors or unusual combinations of conventional phenomena that create the appearance of anomalous behavior. But the possibility that some UAPs might represent extraterrestrial technology cannot be completely dismissed. If even a small fraction of UAP reports represent genuine observations of alien spacecraft, it would be the most important discovery in human history. The challenge for scientists is to investigate these phenomena with appropriate skepticism while remaining open to extraordinary possibilities. This requires developing new methodologies for collecting and analyzing UAP data, establishing standardized reporting protocols, and creating theoretical frameworks for understanding anomalous phenomena. One promising approach is to focus on UAPs that are detected by multiple independent sensors. Military encounters often involve radar observations, infrared cameras, and visual sightings by trained pilots, multiple lines of evidence that make conventional explanations less likely. Scientists are also working to establish networks of automated sensors that could provide continuous monitoring for UAP activity. These networks would use a combination of optical, infrared, and radar sensors to detect and track anomalous objects, providing the kind of systematic data needed for rigorous scientific analysis. The investigation of UAPs has also highlighted the importance of improving our capabilities for detecting and tracking objects in Earth's atmosphere and near-Earth space. Many UAP sightings occur in regions where sensor coverage is limited, making it difficult to obtain the detailed data needed for analysis. Advanced sensor networks, improved radar systems, and space-based monitoring platforms could provide much better coverage of Earth's airspace and help resolve the UAP mystery. These same technologies would also improve our ability to detect potentially hazardous asteroids and other objects in near-Earth space. But the search for extraterrestrial intelligence goes beyond just detecting alien technology. Scientists are also thinking about how we might communicate with extraterrestrial civilizations if we detect their presence. The challenge of interstellar communication is immense. Even our nearest stellar neighbors are more than 4 light-years away, meaning that any exchange of messages would take years or decades. The vast distances involved make real-time conversation impossible and require us to think about communication on timescales far longer than any human endeavor. Despite these challenges, humans have already made several attempts to communicate with potential extraterrestrial civilizations. The Arecibo message, transmitted from the Arecibo radio telescope in 1974, was a pictorial message designed to convey basic information about humanity and Earth to any alien intelligence that might intercept it. The message, targeted at the globular cluster M13, about 25,000 light-years away, contained information about the biochemistry of human life, the structure of DNA, Earth's population, and the solar system. While it will take 25,000 years for the message to reach its target, and another 25,000 years for any reply to return to Earth, it represented humanity's first serious attempt at active communication with extraterrestrial intelligence. More recently, several organizations have undertaken more systematic efforts to transmit messages to potential extraterrestrial civilizations. The organization, Messaging Extraterrestrial Intelligence, METI, has sent multiple messages to nearby star systems, including mathematical concepts, scientific information, and cultural artifacts. But active messaging to extraterrestrial intelligence, also known as active SETI, is controversial within the scientific community. Some scientists argue that revealing our presence to unknown alien civilizations could be dangerous, potentially attracting the attention of hostile aliens who might pose a threat to humanity. Others argue that any civilization advanced enough to travel between stars would likely have already detected our presence through our radio and television broadcasts, which have been leaking into space for more than a century. From this perspective, intentional messages would add little to what aliens could already know about us. The debate over active SETI touches on fundamental questions about humanity's place in the universe and our responsibilities as a potentially communicating civilization. Should we actively seek contact with extraterrestrial intelligence, or should we listen quietly and avoid revealing our presence until we know more about what else might be out there? These questions have led to discussions about developing international protocols for how humanity should respond if we do detect evidence of extraterrestrial intelligence. Various organizations, including the International Academy of Astronautics, have developed draft protocols outlining how the discovery should be verified, announced, and followed up. But creating meaningful protocols for contact with extraterrestrial intelligence is challenging because we have no idea what form such contact might take. A radio signal from space would require different responses than the detection of industrial pollution in an exoplanet's atmosphere, which would require different responses than the discovery of alien artifacts in our solar system. The protocols must also consider the global nature of any contact with extraterrestrial intelligence. Such a discovery would affect all of humanity, not just the scientists or nations involved in the detection. This raises questions about who has the authority to respond on behalf of humanity and how to ensure that the benefits and risks of contact are shared globally. Some scientists have proposed that we should begin preparing for potential contact by developing technologies and institutions that could facilitate communication with extraterrestrial civilizations. This might include building more powerful radio transmitters, developing universal languages based on mathematics and science, and creating international organizations dedicated to managing interstellar communication. Others argue that we should focus first on better understanding potential extraterrestrial civilizations by improving our search capabilities and expanding our knowledge of life in the universe. From this perspective, we should learn as much as possible about alien life before attempting direct communication. The search for extraterrestrial intelligence has also led to speculation about what alien civilizations might be like. The Drake equation, formulated by Frank Drake in 1961, attempts to estimate the number of communicating civilizations in our galaxy by considering factors like the rate of star formation, the fraction of stars with planets, and the likelihood that life will evolve intelligence. Different assumptions about these factors lead to vastly different estimates, ranging from the possibility that we're alone in the galaxy to the possibility that there are millions of technological civilizations. This huge uncertainty reflects our limited understanding of how life originates and evolves, and how commonly intelligence and technology develop. The Fermi Paradox, named after physicist Enrico Fermi, highlights the apparent contradiction between the high probability of extraterrestrial life suggested by the Drake equation and the lack of evidence for such life. If the galaxy should be teeming with civilizations, why haven't we detected any signs of them? Proposed solutions to the Fermi Paradox range from the possibility that intelligent life is extremely rare, to the idea that most civilizations destroy themselves before becoming detectable, to the suggestion that advanced civilizations deliberately hide from younger species like ourselves. One particularly sobering possibility is the Great Filter hypothesis, which suggests that there's some step in the evolution from simple organic compounds to a galaxy-spanning civilization that's incredibly difficult to pass. If this filter is ahead of us, it might explain why we don't see evidence of widespread alien civilizations. But the Great Filter might also be behind us. Perhaps the emergence of life itself, or the evolution of complex cells, or the development of intelligence is so rare that we're among the few species to have overcome these challenges. If so, we might be one of the only technological civilizations in our region of the galaxy. Recent developments in astrobiology and exoplanet science are providing new data that might help resolve some of these questions. The discovery of potentially habitable exoplanets suggests that suitable environments for life might be common. The study of extremophiles on Earth indicates that life can survive in a much wider range of conditions than previously thought. At the same time, our growing understanding of the challenges facing technological civilizations, climate change, resource depletion, nuclear weapons, and other existential risks highlights how difficult it might be for intelligence to survive and thrive over long periods. The search for extraterrestrial intelligence is also being revolutionized by advances in artificial intelligence and machine learning. These technologies are being used to analyze vast datasets from radio telescopes, identify patterns that might indicate artificial signals, and automate the search for techno-signatures. AI systems can process far more data than human researchers and can detect subtle patterns that might be missed by conventional analysis. They can also help filter out interference from human technology and identify candidate signals for follow-up investigation. Machine learning algorithms are being trained to recognize the characteristics of artificial signals and distinguish them from natural astronomical phenomena. These systems can potentially identify types of signals the researchers haven't thought to look for, expanding the scope of SETI searches. But AI also raises new questions about the search for extraterrestrial intelligence. If we develop artificial general intelligence that surpasses human capabilities, how might that change our approach to searching for alien life? And if alien civilizations have also developed advanced AI, how might that affect the types of signals they produce or their interest in communicating with less advanced species? Some researchers have speculated that truly advanced civilizations might transcend biological existence entirely, uploading their consciousnesses into computer systems or merging with artificial intelligence. Such post-biological civilizations might be so different from us that we wouldn't recognize their activities as signs of intelligence. The search for extraterrestrial intelligence is entering a new era of unprecedented capability and scope. Modern telescopes can search millions of star systems simultaneously. Advanced signal processing can detect weaker signals across broader frequency ranges. Space telescopes can study the atmospheres of exoplanets for potential techno-signatures. At the same time, our understanding of life in the universe is rapidly advancing. We're discovering that potentially habitable environments are common in our solar system and beyond. We're learning that life can survive in extreme conditions that were once thought to be completely sterile. We're developing new frameworks for recognizing life that might be very different from terrestrial biology. All of these advances increase our chances of detecting extraterrestrial intelligence, whether through traditional radio searches, optical SET, techno-signature detection, or other methods. The next few decades promise to be the most exciting period in the history of SETI research. But perhaps the most important development is the growing recognition that the search for extraterrestrial intelligence is not just about finding aliens, it's about understanding our own place in the universe. Whether we're alone or part of a vast community of intelligent species, the answer will profoundly shape how we see ourselves and our future. The wow signal remains one of the greatest mysteries in astronomy, a tantalizing hint that we might not be alone in the universe. Whether it was a message from an alien civilization, an unknown natural phenomenon, or something else entirely, it serves as a reminder that the cosmos still holds secrets waiting to be discovered. As we continue our search, using ever more sophisticated tools and techniques, we carry with us the hope that somewhere among the stars, another intelligence is looking back at us, wondering the same questions that have driven humanity to reach for the heavens. Are we alone? And if not, how do we reach out and make contact with our cosmic neighbors? The answer to these questions might be closer than we think. And when we finally make contact, whether through a radio signal, the detection of an artificial atmosphere, or some other means we haven't yet imagined, it will mark the beginning of a new chapter in the story of intelligence in the universe. On a mountaintop in the Atacama Desert of Chile, where the air is so thin and dry that it's considered one of the best astronomical observing sites on Earth, construction crews are putting the finishing touches on what will soon be the most powerful optical telescope ever built. The extremely large telescope, with its 39-meter segmented mirror larger than a basketball court, will have the ability to directly image Earth-sized exoplanets and study their atmospheres in real time, potentially revealing the first definitive signs of life beyond our solar system. This incredible instrument represents just one facet of a revolution in our capability to search for alien life that's already underway. Across the globe, scientists and engineers are developing technologies that would have seemed like pure science fiction just a few decades ago. We're building space telescopes that can analyze the chemical composition of alien atmospheres from thousands of light years away. We're designing robotic submarines that could explore the subsurface oceans of Jupiter's moons. We're even planning to send tiny spacecraft to our nearest stellar neighbor at a significant fraction of the speed of light. The James Webb Space Telescope, which began operations in 2022, has already revolutionized our understanding of exoplanets and their atmospheres. But Webb is just the beginning. The next generation of space telescopes will push our capabilities even further, potentially allowing us to detect not just water vapor and other simple molecules in alien atmospheres, but complex organic compounds and even potential biosignatures. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will use gravitational microlensing to discover thousands of new exoplanets, including many that are too distant or dim to be detected by other methods. This mission will help us understand how common planetary systems like our own really are, and whether Earth-like worlds in habitable zones are typical or rare. Even more ambitious is the proposed Habitable Exoplanet Observatory, HabEx, which would be specifically designed to directly image Earth-sized planets in the habitable zones of nearby stars. Using advanced coronagraph technology to block out the overwhelming light from host stars, HabEx could study the atmospheres of dozens of potentially habitable worlds, searching for the chemical fingerprints of life. The Large Ultraviolet Optical Infrared Surveyor, LUVOIR, another proposed future mission, would be even more powerful. With a mirror up to 15 meters in diameter, LUVOIR could directly image hundreds of exoplanets and characterize their atmospheres in exquisite detail. It could potentially detect seasonal variations that might indicate the presence of vegetation or even pollution signatures that could reveal technological civilizations. But perhaps the most exciting prospect is the possibility of detecting biosignature combinations, multiple molecules in an exoplanet's atmosphere that together provide compelling evidence for life. On Earth, for example, the simultaneous presence of oxygen and methane creates a chemical disequilibrium that's difficult to explain without biological processes. Future telescopes might be sensitive enough to detect similar disequilibria around other worlds. The search for biosignatures is becoming increasingly sophisticated as our understanding of atmospheric chemistry improves. Scientists are developing new theoretical frameworks for interpreting atmospheric compositions, taking into account factors like stellar radiation, planetary dynamics, and geological processes that could affect the chemical signatures we observe. One particularly promising approach is the search for temporal biosignatures, changes in atmospheric composition over time that might indicate biological cycles. On Earth, seasonal variations in carbon dioxide levels are caused by the growth and decay of vegetation. Similar variations on exoplanets could be evidence of alien plant life or other photosynthetic organisms. Another exciting possibility is the detection of biosignature gases that are extremely unlikely to be produced by non-biological processes. Dimethyl sulfide, for example, is produced almost exclusively by marine organisms on Earth. Detecting such molecules in an exoplanet's atmosphere would be very strong evidence for life. The study of exoplanet atmospheres is also being revolutionized by advances in spectroscopy and data analysis. Machine learning algorithms can now extract far more information from spectroscopic observations than was previously possible, potentially allowing us to detect even trace amounts of interesting molecules. New spectroscopic techniques are being developed that could dramatically improve our sensitivity to biosignatures. For example, high-resolution spectroscopy can resolve individual spectral lines with unprecedented precision, potentially allowing us to detect molecules that would be invisible to lower-resolution observations. But the search for alien life isn't limited to distant exoplanets. Some of the most exciting developments are happening right here in our own solar system, where multiple missions are being planned to directly search for life in environments that might be habitable. NASA's Europa Clipper mission, scheduled to launch in the 2020s, will make dozens of flybys of Jupiter's ice-covered moon, studying its subsurface ocean in unprecedented detail. The spacecraft will use ice-penetrating radar to map the thickness and structure of Europa's ice shell, and will analyze any water plumes that might be erupting from the surface. Europa Clipper will carry a suite of sophisticated instruments designed to assess Europa's habitability and search for signs of life. These include mass spectrometers that can analyze the composition of any plume material, cameras that can image the surface in high resolution, and magnetometers that can study the moon's induced magnetic field to better understand the ocean beneath. Even more ambitious is the proposed Europa Lander mission, which would actually touch down on Europa's surface and conduct direct searches for life. The lander would carry instruments capable of detecting organic compounds, analyzing soil samples, and even looking for actual microorganisms that might be present in the ice. Similar missions are being planned for other potentially habitable moons in the outer solar system. The Enceladus Orbilander mission would orbit Saturn's moon Enceladus and then land near its south polar geysers, where it could study the composition of materials ejected from the subsurface ocean. NASA's Dragonfly mission represents perhaps the most ambitious planetary exploration mission ever undertaken. This nuclear-powered helicopter will fly across the surface of Saturn's moon, Titan, studying its complex organic chemistry and searching for signs of life in both the surface hydrocarbon lakes and the subsurface water ocean. Dragonfly will be able to visit multiple sites across Titan's surface, taking advantage of the moon's thick atmosphere and low gravity to fly distances that would be impossible for rovers on other worlds. Each landing site will offer opportunities to study different aspects of Titan's chemistry and potential habitability. The mission will carry instruments capable of analyzing organic compounds in exquisite detail, potentially revealing whether the complex chemistry occurring on Titan's surface has crossed the threshold from non-living to living. If life exists in Titan's methane lakes, Dragonfly might be the mission that discovers it. But perhaps the most exciting development in the search for alien life is the growing possibility of sample return missions that could bring actual alien materials back to Earth for detailed analysis. NASA's Perseverance rover is already collecting samples of Martian rock and soil that will be returned to Earth by a future mission in the 2030s. When those samples finally arrive in terrestrial laboratories, they'll be analyzed with instruments far more sophisticated than anything we can send to Mars. scientists will search for fossilized microorganisms, complex organic molecules that could only be produced by biological processes, and isotopic signatures that might indicate ancient life. The analysis of return Mars samples will likely take years or even decades as scientists carefully study every aspect of the materials using the most advanced analytical techniques available. If these samples contain evidence of ancient Martian life, it would be one of the most important discoveries in human history. Similar sample return missions are being planned for other worlds. The concept for an Enceladus sample return mission would involve a spacecraft that flies through the moon's water plumes, collects organic material, and returns it to Earth for analysis. Such a mission could potentially return actual alien microorganisms if they exist in Enceladus's subsurface ocean. Even more ambitious is the possibility of human missions to Mars and other potentially habitable worlds. While such missions are still decades away, they would provide unprecedented opportunities to search for life using human intelligence and adaptability combined with advanced scientific instruments. Human explorers could access locations that are difficult or impossible for robotic missions to reach, such as deep caves, steep cliffs, or underground water sources. They could make real-time decisions about where to search and what samples to collect, potentially accelerating the pace of discovery dramatically. The development of life support technologies for long-duration space missions is also advancing rapidly. Closed-loop life support systems that recycle air, water, and waste could enable human crews to survive for months or years on Mars or other worlds, providing ample time for thorough biological surveys. But human missions to other worlds also raise important questions about planetary protection. How do we ensure that human explorers don't contaminate alien environments with terrestrial microorganisms? And how do we protect human crews from potential alien pathogens? These challenges are leading to the development of sophisticated sterilization and containment technologies. Future human missions will likely include elaborate procedures for preventing contamination in both directions, ensuring that we can search for alien life without compromising the integrity of either terrestrial or alien ecosystems. The search for alien life is also being revolutionized by advances in artificial intelligence and machine learning. AI systems are already being used to analyze data from SETI searches, identify potentially habitable exoplanets, and process images from Mars rovers. Machine learning algorithms can detect patterns in data that would be impossible for human researchers to identify. They can analyze thousands of exoplanet spectra simultaneously, searching for atmospheric compositions that might indicate habitability or biological activity. AI systems are also being used to design more efficient search strategies. By analyzing the results of previous observations, these systems can identify the most promising targets for future searches and optimize observing schedules to maximize the chances of discovery. In the future, AI might play an even more important role in the search for alien life. Autonomous AI systems could be deployed on spacecraft, making real-time decisions about where to search and what data to collect. Such systems could potentially identify signs of life much more quickly than traditional mission operations that require communication delays of minutes or hours. The development of quantum computing could also revolutionize our search capabilities. Quantum computers could potentially solve complex atmospheric modeling problems that are currently intractable, helping us better understand what biosignatures to look for and how to interpret the observations we make. Quantum sensors could provide unprecedented sensitivity for detecting weak signals or trace molecules that might indicate biological activity. These technologies are still in their early stages, but they hold enormous promise for advancing our search capabilities. The search for alien life is also benefiting from international collaboration on an unprecedented scale. Major space agencies around the world are working together on missions to Mars, Europa, and other potentially habitable worlds. The European Space Agency's JAI-UICE mission will complement NASA's Europa Clipper, providing comprehensive coverage of Jupiter's icy moons. International partnerships are essential for tackling the enormous challenges involved in searching for alien life. No single nation has the resources to explore all the potentially habitable environments in our solar system, let alone search for biosignatures around distant exoplanets. These collaborations are also important for ensuring that the benefits of discovering alien life are shared globally. Such a discovery would be one of the most important in human history, with implications for all of humanity. International cooperation helps ensure that the search is conducted openly and that any discoveries are shared with the global scientific community. But perhaps the most exciting development in the search for alien life is the growing realization that we might be on the verge of answering one of humanity's oldest questions. The combination of advancing technology, increasing understanding of life's requirements, and expanding search capabilities means that we have a realistic chance of detecting alien life within the next few decades. This possibility is driving a new sense of urgency in astrobiology research. Scientists are working to develop the theoretical frameworks needed to interpret potential discoveries of alien life. They're considering how to verify such discoveries and how to communicate them to the public and policymakers. The potential discovery of alien life also raises profound philosophical and societal questions. How would such a discovery change our understanding of life, intelligence, and our place in the universe? How would it affect human religions, philosophies, and worldviews? Some scholars argue that discovering simple microbial life elsewhere would be scientifically revolutionary but might have limited immediate impact on human society. Others suggest that even the discovery of alien microbes would fundamentally change how we see ourselves and our relationship to the cosmos. The discovery of intelligent alien life would almost certainly have much more dramatic impacts. It would raise questions about communication, cooperation, and potential conflicts with alien civilizations. It might spur technological development, inspire new scientific research, or challenge existing power structures. Preparing for these possibilities is becoming an important area of research in its own right. Scholars from fields ranging from astronomy to anthropology are working to understand how humanity might respond to the discovery of alien life and what institutions and protocols might be needed to manage such discoveries. The search for alien life is also driving technological developments that have applications far beyond astrobiology. The sensitive instruments developed for detecting biosignatures can also be used for environmental monitoring on Earth. The life support technologies developed for Mars missions could improve sustainability and resource utilization on our home planet. The communication technologies developed for interplanetary missions are advancing our capabilities for global communications and data transmission. The AI systems developed for analyzing astronomical data are finding applications in fields ranging from medical diagnosis to climate modeling. Perhaps most importantly, the search for alien life is inspiring a new generation of scientists, engineers, and explorers. Young people around the world are pursuing careers in astrobiology, planetary science, and space exploration, motivated by the possibility of making one of the most important discoveries in human history. Educational programs focused on astrobiology are helping students understand the connections between biology, chemistry, physics, and astronomy. These interdisciplinary approaches are training scientists who can tackle complex problems that span multiple fields of study. The public interest in the search for alien life is also driving increased funding for research and exploration. Government agencies, private foundations, and even individual philanthropists are investing billions of dollars in missions and technologies designed to search for life beyond Earth. This investment is accelerating the pace of discovery and enabling increasingly ambitious missions. Projects that would have been considered impossible just a few decades ago are now being seriously planned and funded. The commercialization of space is also opening up new possibilities for the search for alien life. Private companies are developing low-cost launch vehicles, robotic spacecraft, and other technologies that could make space exploration more affordable and accessible. Some private organizations are even funding their own searches for alien life. The Breakthrough Listen project, funded by tech billionaire Yuri Milner, represents the most comprehensive search for extraterrestrial intelligence ever undertaken. Similar private initiatives could accelerate the pace of discovery in the coming years, but the search for alien life also faces significant challenges. The vast distances involved in interstellar exploration mean that even our nearest stellar neighbors are incredibly difficult to reach. Current spacecraft would take thousands of years to reach other star systems, making direct exploration of exoplanets extremely challenging. The technical challenges involved in detecting biosignatures are also enormous. Distinguishing between biological and non-biological sources of potential biosignature molecules requires extremely sophisticated instruments and analysis techniques. The rarity of clear signals or evidence also makes the search difficult. Despite decades of SETI observations, we've detected very few candidate signals, and none have been confirmed as artificial. The search for biosignatures in exoplanet atmospheres is still in its early stages, with only tentative detections reported so far. Funding limitations also constrain the search for alien life. While investment is increasing, the scale of the challenge requires sustained funding over many years or decades. Political and economic pressures can lead to cancellation or delays of important missions. Despite these challenges, the prospects for discovering alien life have never been better. Our understanding of life's requirements and capabilities is advancing rapidly. Our technological capabilities are improving exponentially, and our search strategies are becoming more sophisticated and comprehensive. The next few decades promise to be the most exciting period in the history of astrobiology. Multiple Mars sample return missions will provide unprecedented opportunities to search for evidence of ancient Martian life. Advanced space telescopes will study the atmospheres of potentially habitable exoplanets in detail. Robotic missions will explore the subsurface oceans of Europa, Enceladus, and other icy moons. Each of these endeavors has the potential to answer the fundamental question of whether we're alone in the universe. And if the answer is that we're not alone, it will open up entirely new fields of scientific research and exploration. The discovery of alien life would also likely accelerate technological development and space exploration. The confirmation that life exists elsewhere would provide strong motivation for developing interstellar travel capabilities and establishing permanent human settlements beyond Earth. It might also lead to new insights into the nature of life itself. Studying alien biochemistry could reveal new principles of biology and potentially inspire new technologies based on biological processes. The search for alien life represents humanity at its best, our curiosity, our ingenuity, and our determination to understand our place in the universe. Whether we discover abundant life throughout the cosmos or confirm that Earth is unique, the search itself is expanding our knowledge and capabilities in profound ways. As we stand on the threshold of potentially discovering that we're not alone, we should remember that the journey is as important as the destination. The search for alien life is teaching us about the nature of life, the formation and evolution of planetary systems, and the chemical and physical processes that govern the universe. It's also bringing humanity together in a common endeavor that transcends national boundaries and cultural differences. The search for alien life is truly a global enterprise involving scientists and engineers from around the world working toward a common goal. And perhaps most importantly, the search for alien life is giving us a new perspective on our own planet and our responsibility to protect it. As we learn about the rarity and fragility of life in the universe, we develop a deeper appreciation for the life we have here on Earth. The future of the search for alien life is bright. New technologies, new missions, and new discoveries are bringing us closer to answering one of humanity's oldest questions. Whether we're alone or part of a vast community of life in the universe, the answer will fundamentally change how we understand ourselves and our place in the cosmos. The universe has been waiting 13.8 billion years to ask this question through us, and we're finally in a position to answer it. What we discover will echo through the corridors of time and space, changing forever how intelligence understands its place in the cosmos. Are we alone? We're about to find out. And when we do, everything changes, the search continues, the answer awaits, and the universe holds its breath, waiting to reveal its deepest secrets to those brave enough to seek them. This is humanity's greatest adventure. This is our cosmic destiny. This is the search for alien life, and you, right now, are part of it. You're living through one of the most important periods in human history, the time when we first seriously searched for life beyond Earth. You're witnessing the development of technologies that could reveal whether we're alone in the universe. You're part of the generation that might finally answer the question that has haunted humanity since we first looked up at the stars and wondered, are we alone? The answer to that question, whatever it turns out to be, will be one of the defining discoveries of our species. It will reshape our understanding of life, intelligence, and our place in the cosmic story. It will influence our philosophy, our religion, our science, and our future as a civilization. And we might not have to wait much longer to find out. The pace of discovery in astrobiology is accelerating rapidly. Every year brings new exoplanet discoveries, new insights into the requirements for life, and new technologies for detecting biological signatures across vast distances. Whether we find microbes in the subsurface oceans of Europa, detect biosignatures in the atmosphere of a distant exoplanet, or receive a radio signal from an alien civilization, the discovery will mark the end of our cosmic loneliness and the beginning of a new chapter in the story of life in the universe. So as you go about your daily life, remember that you're living at a special time in history. You're alive during humanity's first serious attempt to answer one of our oldest and most profound questions. You're witnessing the birth of a new scientific age when we'll finally know whether Earth is unique or part of a living universe. The stars are calling to us, as they've called to every generation of humans who have ever lived. But for the first time in our species' history, we have the tools to answer their call. We have the technology to search for life among the stars, and we're using it. The search for alien life is more than just a scientific endeavor. It's a quest to understand our place in the universe, to learn whether we're alone or part of something much larger than ourselves. It's humanity's greatest adventure, and you're part of it. The universe is vast, ancient, and full of possibilities we're only beginning to explore. Somewhere out there, in the depths of space, or perhaps closer than we imagine, the answer to our question might be waiting. And when we find it, when we finally know whether we're alone, it will change everything. The search continues, the future awaits, and the greatest discovery in human history might be just around the corner. Epilogue, the moment of contact, extended conclusion. But let me paint you a picture of what that moment might actually look like when it finally arrives. Imagine you're watching the news one evening when a special bulletin interrupts regular programming. The anchor's voice is steady, but there's an unmistakable tremor of excitement as they announce that scientists at the European Southern Observatory have detected something extraordinary in the atmosphere of Proxima Centauri. The initial detection came from the James Webb Space Telescope during a routine observation. As the planet passed in front of its star, Webb's sophisticated spectrometers analyzed the starlight filtering through the alien atmosphere. What they found was a combination of gases that shouldn't exist together unless something was actively producing them: oxygen, water vapor, and most remarkably, a molecule called dimethyl sulfide that on Earth is produced almost exclusively by marine plankton. The Discovery team spent months verifying their results, running the data through every possible filter, checking for instrumental errors, and considering every conceivable non-biological explanation. They brought in experts from around the world to review their analysis. They observed the planet again with different instruments, confirming the original detection. And slowly, inevitably, they reached the conclusion that would change everything. They had found the first definitive evidence of life beyond Earth. The announcement sends shockwaves around the world. Stock markets fluctuate wildly as investors try to process the implications. Religious leaders issue statements grappling with what alien life means for their faiths. Scientists work around the clock to design follow-up observations that might tell us more about these alien organisms. But here's what's truly remarkable about this scenario. It's not science fiction. Every technology I just described either already exists or is currently under development. The James Webb Space Telescope is already observing exoplanet atmospheres. The techniques for detecting atmospheric biosignatures are being refined every day. Proxima Centauri b is a real planet, orbiting the nearest star to our Sun, waiting for us to study it in detail. This discovery could happen next year. It could happen next week. It could be happening right now, in the data flowing back from Webb or from one of the many other telescopes searching for signs of life among the stars. And this is just one possible scenario. the first detection of alien life might come from much closer to home. Picture a different scene: a team of scientists hunched over computer screens at NASA's Jet Propulsion Laboratory, analyzing the latest data from the Europa Clipper mission. The spacecraft had been studying Jupiter's ice-covered moon for months, flying through the water plumes that occasionally erupt from its surface. On this particular day, the mass spectrometer data shows something unprecedented. Mixed in with the water and simple organic compounds that the scientists expected to find, there are more complex molecules, amino acids, lipids, and most shocking of all, something that looks unmistakably like DNA or RNA fragments. The plumes aren't just venting sterile ocean water, they're carrying the molecular signatures of living organisms. The implications hit the team immediately. Europa's subsurface ocean, that dark sea hidden beneath miles of ice, isn't just habitable, it's inhabited. Somewhere in those alien waters, life forms are swimming, reproducing, evolving, completely unaware that their existence is about to become the most important discovery in human history. Or consider this scenario: you're listening to the radio during your morning commute when the emergency alert system interrupts with a special announcement. The Breakthrough Listen project has detected a clearly artificial signal from the star system Tau Ceti, just 12 light-years away. The signal is structured, mathematical, clearly designed, unmistakably the product of an intelligent civilization. As you pull over to listen more carefully, the announcer explains that the signal appears to be a response to radio transmissions that Earth sent into space decades ago. Someone, or something, out there has been listening to our broadcasts, learning our languages, understanding our science, and now they're talking back. The signal contains mathematical concepts, prime numbers, and what appear to be basic scientific constants, a cosmic Rosetta Stone designed to establish that its creators understand the fundamental laws of physics. But embedded within these mathematical messages are hints of something more, patterns that suggest art, music, perhaps even poetry. We're not just looking at evidence of alien intelligence, we're looking at the first examples of alien culture. These scenarios might sound like fantasy, but they're all within the realm of possibility given our current and near-future capabilities. The instruments exist. The techniques are proven. The targets are identified. All we need is for life to actually be out there waiting to be found. But what happens after that first detection? How does humanity change when we know, definitively, that we're not alone? The immediate effects would be profound. The scientific community would mobilize like never before, with every major space agency and research institution shifting resources towards studying the newly discovered life. New missions would be planned and funded at unprecedented speeds. The discovery of life on Europa might trigger a crash program to land submarines in that alien ocean within a decade, rather than the usual multi-decade timescales of space missions. The detection of a biosignature around Proxima Centauri b would likely accelerate efforts to send probes to that star system. Projects like Breakthrough Starshot, which proposes using powerful lasers to accelerate tiny spacecraft to 20% the speed of light, might receive massive new funding. Humanity would suddenly have a specific target for interstellar exploration, a known living world just 4.2 light-years away. The detection of an artificial signal would trigger the protocols that SETI scientists have been developing for decades. The signal would be verified by observatories around the world. The United Nations would convene special sessions to discuss humanity's response. We would face the unprecedented challenge of deciding how to answer and what message we want to send on behalf of our entire species. But the long-term effects might be even more profound. The knowledge that life exists elsewhere would fundamentally change how we see ourselves and our place in the universe. We would no longer be alone, isolated on a small planet in a vast, cold cosmos. We would be part of something larger, a community of life that spans the galaxy and perhaps the universe. This shift in perspective could have powerful effects on human society. Knowing that life is possible elsewhere might make us more committed to preserving life on Earth. The realization that we're part of a larger cosmic community might help us overcome the divisions that separate nations, cultures, and ideologies here on our home planet. The discovery of alien life would also likely accelerate scientific and technological development. Understanding how life evolved independently on another world would provide new insights into biology, chemistry, and the fundamental processes that govern living systems. Studying alien biochemistry might lead to new medicines, new materials, and new technologies we can't even imagine. If we discover intelligent alien life, the implications become even more profound. Communication with an alien civilization, even across the vast distances of interstellar space, would provide access to knowledge and perspectives that are completely alien to human experience. And civilization that's existed for millions of years longer than ours might have solved problems that we're just beginning to grapple with. Climate change, resource scarcity, social organization, perhaps even the fundamental questions of consciousness and existence. But alien contact would also raise challenging questions. How would we verify that communications are really coming from aliens and not from some elaborate hoax? How would we establish trust with a civilization that we know nothing about? How would we ensure that the benefits and risks of contact are shared fairly among all of humanity? There would also be risks to consider. While most scientists believe that any civilization capable of interstellar communication would likely be peaceful, violent species, tend to destroy themselves before achieving such advanced technology, we can't be certain. The history of contact between human civilizations offers sobering lessons about what can happen when more advanced societies encounter less advanced ones. Even peaceful contact could be disruptive. The knowledge that far more advanced civilizations exist elsewhere might diminish human achievements and aspirations. Some people might become fatalistic, feeling that human progress is meaningless in the face of vastly superior alien technology. Others might become obsessed with trying to communicate with or travel to these alien civilizations, potentially at the expense of solving problems here on Earth. These challenges would require new institutions and new forms of international cooperation. We might need a global authority for managing alien contact, similar to how we now have international organizations for managing nuclear weapons or addressing climate change. We might need new legal frameworks for dealing with alien technology or information. But despite these challenges, most scientists and philosophers believe that discovering alien life would ultimately benefit humanity. It would expand our knowledge, broaden our perspectives, and provide new opportunities for growth and development. It would mark the beginning of a new chapter in human history, the chapter where we become a truly cosmic species, aware of our place in a universe teeming with life and intelligence. The search for alien life has already changed us in profound ways. It has driven technological innovation, inspired international cooperation, and given us new perspectives on the preciousness and fragility of life on Earth. The actual discovery of alien life would accelerate all of these trends, ushering in a new era of human development and cosmic awareness. As we stand on the threshold of this discovery, it's worth reflecting on the journey that has brought us here. For thousands of years, humans have wondered whether we're alone in the universe. For the first time in our species' history, we have the tools and techniques to answer that question definitively. We've built telescopes that can peer into the atmospheres of worlds orbiting other stars. We've sent robots to explore the subsurface oceans of distant moons. We've listened to the cosmos with radio telescopes searching for any sign that someone else is out there. We've studied life in the most extreme environments on Earth, learning that biology is far more resilient and adaptable than we ever imagined. All of this work has been building toward a single moment, the moment when we finally detect clear, unambiguous evidence of life beyond Earth. That moment might come tomorrow, or next year, or sometime in the next few decades. But it's coming, and when it arrives, it will be the most important discovery in human history. The universe has been waiting 13.8 billion years for intelligence to evolve somewhere, to develop science and technology, to build instruments capable of detecting life across the vast distances of space. That intelligence is us. We are the universe's way of knowing itself, of searching for life, of asking the fundamental questions about existence and consciousness and meaning. And now, finally, we're on the verge of finding answers. The search for alien life has taken us on an incredible journey of discovery, revealing the diversity and resilience of life on Earth, the vast number of potentially habitable worlds in our galaxy, and the sophisticated technologies needed to search for biosignatures across interstellar distances. Whether we find abundant life throughout the cosmos or learn that Earth is unique, the search itself has expanded our understanding of life, the universe, and our place within it. It has united humanity in a common quest that transcends national boundaries and cultural differences. It has inspired new generations of scientists and explorers, and it has given us a deeper appreciation for the remarkable planet we call home. But I believe we will find life out there. The universe is too vast, too rich in potentially habitable environments for Earth to be the only living world. The same physical and chemical processes that gave rise to life here have been operating throughout the cosmos for billions of years. The ingredients for life, water, organic compounds, energy sources, are abundant throughout the universe. Life, it seems, is not an accident, but an inevitable consequence of the right conditions. And those conditions exist on countless worlds throughout our galaxy and beyond. We're not alone. We never were. We just needed to develop the technology and wisdom to recognize our cosmic companions. The discovery that we're not alone will mark the end of one era and the beginning of another. It will close the chapter of human history when we wondered whether we were unique in the universe. And it will open a new chapter, the chapter where we learn to live as part of a vast, living cosmos, where we explore and understand and perhaps even communicate with our fellow travelers in the great adventure of existence. The stars are calling to us, as Carl Sagan once said, and finally, we're ready to answer. The search for alien life represents humanity at its best. Our curiosity, our ingenuity, our determination to understand our place in the cosmos. It's a quest that has already transformed our understanding of life and the universe, and it promises to deliver the most important discovery in human history. Are we alone? The answer is waiting out there in the darkness between the stars, in the hidden oceans beneath icy moons, in the atmospheres of distant worlds. And we're going to find it. The greatest adventure in human history is just beginning. The search for alien life continues, and the universe is about to reveal its most profound secret, that life, in all its magnificent diversity, is woven into the very fabric of existence itself. We are not alone. We never were, and soon, very soon, we'll know it for certain. The cosmos is alive, and we're about to prove it. Extended exploration, the many faces of alien life. But what would alien life actually look like? This question has fascinated scientists and science fiction writers for decades, but as our understanding of biology and planetary environments has advanced, we're developing increasingly sophisticated ideas about the forms that alien life might take. Consider the subsurface ocean of Europa. This alien sea has been isolated from the surface for potentially billions of years, existing in eternal darkness beneath miles of ice. Any life that evolved in this environment would be fundamentally different from anything on Earth's surface. These creatures would never have seen sunlight, never experienced weather, never known the rhythm of day and night. In Europa's ocean, life might cluster around hydrothermal vents on the seafloor, just as it does in Earth's deep oceans. But these alien ecosystems could be far more extensive than anything on our planet. Without the competing energy source of sunlight, chemosynthetic life might dominate Europa's ocean completely, creating vast networks of organisms that process chemicals from the moon's rocky core. Imagine alien creatures that are essentially living chemical factories, organisms that have evolved to process the complex chemistry of Europa's ocean with an efficiency that puts terrestrial life to shame. These beings might communicate through chemical signals, creating clouds of molecular messages that spread through the ocean like an alien internet. Some of these organisms might be tiny, microscopic bacteria-like creatures that form vast mats across the ocean floor. Others might be larger, more complex organisms that have evolved to exploit specific chemical niches in the ocean's ecosystem. There might even be large, mobile organisms, alien whales, if you will, that migrate through Europa's ocean following chemical gradients and feeding on smaller organisms. But Europa's life might also take forms that are completely alien to our experience. Without the constraints of surface gravity and atmospheric pressure, organisms might evolve into shapes and structures that would be impossible on Earth. There might be creatures that are essentially living geometric structures, organisms whose bodies are organized according to mathematical principles rather than the bilateral symmetry that dominates terrestrial life. the high pressure and low temperature of Europa's ocean might favor very different biochemical strategies than those used by Earth life. Proteins might be stabilized by different chemical bonds, allowing for molecular machines that work in ways completely foreign to terrestrial biochemistry. The organisms might use antifreeze compounds so sophisticated that they can remain active at temperatures well below the freezing point of pure water. But Europa is just one possibility. Consider the even more alien environment of Titan's hydrocarbon seas. If life exists in these methane and ethane lakes, it would be based on completely different chemistry than anything we know. These organisms would use liquid methane as their primary solvent instead of water, and their biochemistry would be built around carbon-hydrogen chains rather than carbon-oxygen bonds. Titanian life might be incredibly slow by Earth standards, operating at the leisurely pace allowed by the Moon's frigid temperatures. Chemical reactions that take milliseconds in terrestrial organisms might take hours or days in Titan's cold environment. These aliens might live for thousands or even millions of years, their metabolism so slow that they experience time on geological scales. But this slow metabolism might also allow for incredible complexity. With millions of years to develop and refine their molecular machinery, Titanian organisms might achieve levels of biochemical sophistication that dwarf anything on Earth. They might be living computers, organisms whose bodies are essentially biological microprocessors capable of incredibly complex information processing. The visual systems of Titanian life would also be completely different from anything on Earth. Titan's thick atmosphere filters out most visible light, but infrared radiation penetrates more easily. Any organisms that evolved vision would likely see in the infrared spectrum, perceiving a world of heat and thermal gradients invisible to human eyes. These creatures might have evolved to detect the faint infrared glow of Titan's surface geology, using thermal vision to navigate the Moon's landscape of hydrocarbon dunes and methane rivers. They might even be able to see the aurora that occasionally dance in Titan's upper atmosphere, caused by Saturn's magnetic field interacting with the solar wind. But perhaps the most intriguing possibility is that Titanian life might have evolved forms of communication based on the Moon's unique acoustic properties. Titan's thick atmosphere is excellent at transmitting sound, and organisms might have evolved sophisticated acoustic communication systems that allow them to communicate across vast distances. Imagine alien songs echoing across Titan's methane seas, complex acoustic patterns that carry information about food sources, mating opportunities, and environmental conditions. These organisms might create a symphony of alien music that plays continuously across the Moon's surface, a cosmic concert that has been running for millions of years without any audience, until now. Moving beyond our solar system, the possibilities become even more exotic. The exoplanet TRAPPIST-1e, located about 40 light-years from Earth, orbits a red dwarf star so close that it's likely tidally locked, with one side permanently facing the star and the other side permanently dark. Life on such a world would have to contend with extreme temperature differences between the day and night sides. But this challenge might lead to fascinating evolutionary solutions. Organisms might migrate constantly between the day and night sides, following the temperature gradients to maintain optimal body temperatures. There might be vast migrations of alien creatures moving in slow processions around the planet to stay within the narrow twilight zone where temperatures are suitable for life. Or life might evolve to exploit the extreme temperature differences directly. Organisms might function like biological heat engines, using the temperature gradient between the hot and cold sides of the planet to power their metabolism. These creatures would literally feed on temperature differences, converting thermal energy into the chemical energy needed for life. The atmospheric dynamics of tidally locked planets also create unique opportunities for life. The constant temperature differences drive powerful winds that circle the planet, and organisms might evolve to ride these atmospheric currents like aerial plankton. There might be entire ecosystems floating in the planet's atmosphere, communities of organisms that spend their entire lives airborne. These atmospheric organisms might be incredibly lightweight, possibly even gas-filled like balloons, allowing them to remain aloft indefinitely. They might feed on chemicals in the atmosphere or use some form of aerial photosynthesis to capture energy from the star's radiation. Some might be microscopic, while others could be vast aerial creatures comparable to Earth's largest whales. But perhaps the most alien life would be found on planets orbiting different types of stars. Red dwarf stars, which make up about 75% of all stars in the galaxy, produce much more infrared radiation relative to visible light than our Sun does. Life evolving around these stars might use completely different forms of photosynthesis, capturing energy from infrared photons rather than visible light. Such organisms might appear black or dark red to human eyes, having evolved pigments that efficiently absorb infrared radiation. Their version of photosynthesis might be so different from Earth's that we might not even recognize it as a form of energy capture initially. Even more exotic would be life around massive hot stars that produce large amounts of ultraviolet radiation. Organisms evolving in such environments might have incredibly sophisticated UV protection systems, possibly using fluorescent compounds to convert harmful UV radiation into usable energy. These aliens might literally glow in the dark, their bodies shining with converted starlight. Some scientists have even speculated about life that could exist in the atmospheres of gas giant planets. Jupiter and Saturn have regions in their atmospheres where temperatures and pressures are Earth-like and complex organic chemistry is known to occur. Could there be organisms floating in these alien skies, feeding on atmospheric chemicals and reproducing in the perpetual twilight of the gas giants' atmospheres? Such atmospheric life would face unique challenges. Without solid surfaces to anchor to, these organisms would need to be neutrally buoyant, possibly using gas-filled organs to control their altitude in the atmosphere. They might reproduce by releasing spores into the atmospheric currents, spreading their offspring across vast regions of the planet. The largest of these atmospheric organisms might be truly gigantic, possibly larger than any creature that has ever lived on Earth. Without the structural constraints imposed by gravity and solid surfaces, aerial life forms might grow to enormous sizes, becoming living clouds that drift through alien skies. But life might also exist in environments that are even more extreme than planetary atmospheres. Some scientists have speculated about organisms that could survive in the vacuum of space itself, possibly using cosmic radiation as an energy source. Such life would be incredibly diffuse, possibly existing as vast networks of interconnected organisms spread across solar systems. These space-dwelling organisms might be so different from terrestrial life that we wouldn't recognize them as living at all. They might exist as self-organizing patterns in plasma or electromagnetic fields, using the energy of stellar radiation to maintain their structure and reproduce. Even more speculative is the possibility of life existing in exotic astrophysical environments, like the accretion disks around black holes or the interiors of neutron stars. While such environments seem impossibly hostile to life as we know it, they contain enormous amounts of energy and complex physical processes that might, under the right circumstances, give rise to forms of organization that could be considered alive. The search for such exotic life forms would require completely new detection strategies and theoretical frameworks. We would need to expand our definition of life to include systems that might not be based on chemistry at all, but rather on plasma physics, quantum mechanics, or other fundamental processes. But let's return to more immediate possibilities. As we develop better techniques for studying exoplanet atmospheres, we're beginning to identify chemical signatures that might indicate not just life, but specific types of life. Different metabolic processes produce different waste products, and these molecular signatures might allow us to infer what kinds of organisms exist on distant worlds. For example, the detection of large amounts of oxygen in an exoplanet's atmosphere would suggest the presence of photosynthetic organisms similar to Earth's plants and cyanobacteria. But the detection of other gases might indicate completely different forms of life. Methane could indicate the presence of organisms similar to Earth's methanogens, bacteria that produce methane as a waste product. But it could also indicate much more complex ecosystems, since methane is produced by many different biological processes. The detection of hydrogen sulfide might indicate life similar to the chemosynthetic bacteria found around Earth's hydrothermal vents. The presence of ammonia could suggest organisms that use different nitrogen chemistry than terrestrial life. Even more intriguing would be the detection of gases that don't occur naturally in significant quantities. Dimethyl sulfide, as mentioned earlier, is produced almost exclusively by marine organisms on Earth. Its detection in an exoplanet atmosphere would be very strong evidence for oceanic life. Other potential biosignature gases include phosphine, which is produced by anaerobic organisms on Earth, and various organic sulfur compounds that are associated with biological processes. The key is finding combinations of gases that are difficult to explain through non-biological processes. But future telescopes might be able to detect even more subtle signs of life. Seasonal variations in atmospheric composition could indicate biological cycles, such as the growth and decay of vegetation. Daily variations might indicate the presence of organisms that are active during specific parts of the planet's day-night cycle. Some scientists have even proposed looking for the spectroscopic signatures of chlorophyll or other photosynthetic pigments in the light reflected from exoplanets. While this would be incredibly challenging to detect, it would provide direct evidence for photosynthetic life. The search for biosignatures is also becoming more sophisticated in terms of understanding false positives. Many molecules that could be produced by life can also be produced by non-biological processes, and distinguishing between these possibilities requires careful analysis of the planetary environment. For example, oxygen can be produced by the photodissociation of water molecules by stellar radiation, not just by photosynthesis. But photodissociation would also produce large amounts of hydrogen, which would escape to space, leaving behind other chemical signatures that could distinguish this process from biological oxygen production. Similarly, methane can be produced by geological processes, but biological methane production typically creates specific isotopic ratios that might be detectable with sufficiently sensitive instruments. The challenge is developing theoretical models that can account for all the possible chemical and physical processes that might affect an exoplanet's atmosphere, allowing us to identify the signatures that can only be explained by biological activity. This is leading to the development of increasingly sophisticated atmospheric models that take into account factors like stellar radiation, atmospheric dynamics, surface geology, and possible biological processes. These models help scientists understand what biosignatures to look for and how to interpret the observations they make. But perhaps the most exciting development is the realization that we might be able to detect not just simple life, but complex ecosystems and even intelligent civilizations through atmospheric analysis. A planet with a complex biosphere might show seasonal variations in multiple atmospheric components, indicating the presence of different organisms with different life cycles. The atmosphere might show signs of coevolution between different types of organisms, such as the production of oxygen by some organisms and its consumption by others. Even more intriguingly, we might be able to detect industrial pollution in exoplanet atmospheres. Chlorofluorocarbons, CFCs, nitrogen dioxide, and other industrial compounds would be clear evidence of technological activity. While current telescopes aren't sensitive enough to detect these signatures, future instruments might be able to identify the atmospheric fingerprints of alien civilizations. The detection of artificial lighting on the night side of exoplanets is another possibility. A civilization that had developed electric lighting on a global scale would create a detectable signature in the planet's infrared emission. This would be an unambiguous technosignature, since no natural process could create the spectral characteristics of artificial lighting. Large-scale planetary engineering projects might also be detectable through atmospheric analysis. A civilization that was terraforming their planet or managing its climate might create atmospheric compositions that are clearly artificial, with molecular ratios that couldn't occur naturally. Some scientists have even proposed looking for atmospheric signatures of space elevators, orbital habitats, or other megastructures. While these would be extremely challenging to detect, they represent the kinds of technosignatures that sufficiently advanced civilizations might inadvertently create. The search for these advanced technosignatures requires thinking about what kinds of projects a technological civilization might undertake and what atmospheric signatures these projects might create. This is leading to new interdisciplinary collaborations between astronomers, atmospheric scientists, and even economists and sociologists who can help predict what advanced civilizations might do. But even if we detect clear evidence of life or intelligence around other stars, actually studying these alien organisms in detail would require technologies that don't yet exist. Interstellar travel remains one of the greatest challenges facing humanity, but recent developments are making it seem more feasible than ever before. The Breakthrough Starshot project proposes using powerful lasers to accelerate tiny spacecraft to about 20% the speed of light, allowing them to reach Proxima Centauri in about 20 years. While these spacecraft would be incredibly small, roughly the size of a computer chip, they could carry miniaturized cameras, spectrometers, and communication equipment that would allow them to study the Proxima Centauri system in detail. If Proxima Centauri b does harbor life, these tiny probes could potentially detect it directly, sending back close-up images and spectroscopic data that would revolutionize our understanding of alien biology. Even if the probes only made a brief flyby of the planet, the data they collected would be invaluable. But Breakthrough Starshot is just the beginning. More ambitious interstellar missions are being conceptualized that could carry larger payloads and even return samples to Earth. These missions would take much longer, hundreds or thousands of years, but they could provide unprecedented opportunities to study alien life directly. Some concepts involve self-replicating spacecraft that could build copies of themselves using materials found in the target star system. These von Neumann probes could potentially establish permanent research stations around other stars, continuously studying alien worlds and transmitting data back to Earth. Even more speculative are concepts for faster-than-light travel or communication. While these remain in the realm of theoretical physics, recent advances in our understanding of quantum mechanics and general relativity are suggesting new possibilities for manipulating space and time. Quantum entanglement, for example, might allow for instantaneous communication across interstellar distances, even if it doesn't allow for faster-than-light travel. This could enable real-time communication with interstellar probes or even with alien civilizations. The study of exotic matter and energy, including concepts like wormholes and Alcubierre drives, is also advancing. While these technologies remain highly speculative, they represent potential pathways to practical interstellar travel that could dramatically reduce the time required to reach other star systems. But even with current technology, we could potentially send much more ambitious missions to the outer solar system to study the potentially habitable moons of Jupiter and Saturn. Nuclear-powered spacecraft could carry sophisticated instruments to Europa, Enceladus, and Titan, including landing systems that could penetrate their ice shells and deploy submersibles in their subsurface oceans. Imagine a robotic submarine exploring Europa's alien sea, its lights illuminating strange formations on the ocean floor, and its cameras recording the first images of swimming alien organisms. Such a mission could answer fundamental questions about the nature of life and the possibilities for evolution in environments completely different from Earth. The technology for such missions is largely within our current capabilities. Nuclear thermal propulsion could reduce travel times to the outer solar system from decades to years. Advanced life support systems could enable long-duration missions. Autonomous navigation and communication systems could allow spacecraft to operate independently across the vast distances of the outer solar system. What's really needed is the political will and financial commitment to undertake these ambitious missions. The discovery of life elsewhere in our solar system would be so scientifically and culturally significant that it would likely trigger massive new investments in space exploration and astrobiology research. But the search for alien life isn't just about technology, it's also about developing new theoretical frameworks for understanding what life is and how it might manifest under different conditions. This requires collaboration between biologists, chemists, physicists, and even philosophers and computer scientists. One emerging field is called agnostic biosignature detection, the development of techniques for recognizing life that don't depend on assumptions about its chemistry or metabolism. Instead of looking for specific molecules like oxygen or methane, these approaches look for patterns of complexity, organization, or disequilibrium that might indicate the presence of living systems. For example, all living systems must maintain themselves against entropy, creating local decreases in entropy at the expense of increasing entropy in their environment. This fundamental characteristic of life might be detectable even if the specific chemistry is completely alien. Similarly, living systems tend to create patterns of chemical or physical organization that are highly unlikely to occur through random processes. Machine learning algorithms are being developed that can recognize these patterns of biological complexity without prior knowledge of what they should look like. These approaches might allow us to detect forms of life that are so alien that we wouldn't recognize them using traditional biosignature searches. They could potentially identify living systems based on silicon chemistry, exotic solvents, or even non-chemical processes that we haven't imagined. The development of these agnostic detection methods is also important for understanding life on Earth. By studying the fundamental principles that distinguish living from non-living systems, we're gaining new insights into the nature of biology itself. This work is leading to new definitions of life that are more general and more rigorous than previous attempts. Instead of focusing on specific chemical processes, these definitions emphasize the information processing and self-organizational capabilities that seem to be fundamental to all living systems. Understanding these principles is crucial for recognizing alien life when we encounter it. If life is truly a universal phenomenon, then it should exhibit these fundamental characteristics regardless of its specific chemistry or environment. But the search for alien life also raises profound philosophical questions about consciousness, intelligence, and the meaning of existence. If we discover that life is common throughout the universe, what does that say about the significance of human consciousness? Some philosophers argue that the discovery of alien life would diminish the special status of humanity, showing that we're not unique in the cosmos. Others suggest that it would enhance our significance, demonstrating that consciousness and intelligence are fundamental features of the universe rather than accidents of evolution. The detection of alien intelligence would raise even more complex questions. How would we evaluate the moral status of alien beings? Do we have obligations toward them? How would we resolve conflicts between human and alien interests? These questions are becoming increasingly urgent as our search capabilities improve and the possibility of detecting alien life becomes more real. Philosophers, ethicists, and legal scholars are beginning to develop frameworks for thinking about these issues before they become practical concerns. Some have proposed extending concepts of rights and moral consideration to include potential alien life forms. Others have suggested developing new ethical frameworks specifically designed to address the unique challenges of interspecies contact. The legal implications are equally complex. Who owns resources on planets that harbor alien life? How do we regulate human activities that might affect alien ecosystems? What legal frameworks would govern communication or trade with alien civilizations? International law currently has very limited provisions for dealing with alien life, and developing new legal frameworks will require unprecedented international cooperation. The discovery of alien life would truly be a global event requiring global responses. But perhaps the most profound impact of discovering alien life would be on human culture and consciousness. Such a discovery would likely trigger a renaissance in art, literature, philosophy, and science that could rival the greatest cultural transformations in human history. Artists and writers would be inspired by the reality of alien life to create new forms of expression that incorporate truly cosmic perspectives. Musicians might compose symphonies inspired by the sounds of alien worlds or the mathematics of interstellar communication. Philosophers would grapple with new questions about the nature of existence, consciousness, and meaning in a universe known to harbor other minds. Religious leaders would need to develop new theological frameworks that account for the reality of alien life. Scientists would face the challenge of developing entirely new fields of study to understand alien biology, alien intelligence, and alien civilizations. The study of comparative biology would expand to include organisms from completely different evolutionary lineages. The study of intelligence would need to account for minds that might work according to completely different principles than human cognition. All of these cultural and intellectual developments would likely accelerate human progress in numerous fields. The challenge of understanding alien life would drive innovations in biology, chemistry, physics, and computing. The goal of communicating with alien intelligence would spur advances in mathematics, linguistics, and information theory. The economic implications would also be enormous. New industries would emerge around the study and exploration of alien life. Space exploration would likely receive massive new investments. International cooperation would increase as nations recognize the global importance of astrobiology research. Some economists have speculated that the discovery of alien life could trigger a new economic boom comparable to the Industrial Revolution or the Digital Revolution. The technological challenges involved in studying and communicating with alien life would require innovations that could have applications throughout human society. But the discovery of alien intelligence could also pose economic challenges. If alien civilizations possess far more advanced technology than ours, how would human economies adapt? How would we maintain human relevance in a universe where far more advanced minds exist? These questions are already being discussed by economists and futurists who recognize that technological advancement, whether by humans or aliens, will continue to reshape human society in fundamental ways. The geopolitical implications would be equally significant. The discovery of alien life would likely accelerate international cooperation in space exploration and scientific research, but it might also create new sources of competition and conflict as nations vie for leadership in astrobiology and interstellar exploration. The country or organization that first detects alien life would gain enormous prestige and influence. This creates incentives for increased investment in astrobiology research and space exploration capabilities. It also raises questions about how such discoveries should be managed and shared. Some have proposed that the search for alien life should be conducted under international auspices, ensuring that any discoveries benefit all of humanity rather than individual nations. Others argue that competition between nations will accelerate progress and increase the likelihood of success. These debates are becoming more urgent as multiple countries develop advanced space exploration capabilities. China, India, and other nations are launching increasingly ambitious missions to study potentially habitable worlds. Private companies are also entering the field, adding another layer of complexity to the international landscape. The management of potential alien contact is becoming a serious policy issue that requires input from scientists, diplomats, lawyers, and philosophers. The stakes are too high to leave these decisions to chance or to individual institutions. As we stand on the threshold of potentially discovering alien life, we need to prepare not just technologically, but also intellectually, culturally, and institutionally. The discovery of alien life would be one of the most important events in human history, and we need to be ready for its implications. This preparation involves not just building better telescopes and spacecraft, but also developing new ways of thinking about life, intelligence, and our place in the universe. It requires international cooperation on an unprecedented scale. It demands that we think seriously about the ethical, legal, and philosophical implications of contact with alien life. But, perhaps most importantly, it requires that we maintain our sense of wonder and curiosity about the universe. The search for alien life is driven by the same curiosity that has always motivated human exploration and discovery. It represents our desire to understand our place in the cosmos and to know whether we share this vast universe with other thinking beings. That curiosity has already transformed our understanding of life and the universe. It has driven technological innovations that benefit all of humanity. It has inspired new generations of scientists and explorers, and it has given us a deeper appreciation for the remarkable planet we call home. Whether we ultimately discover that life is abundant throughout the universe or that Earth is unique, the search itself is valuable. It expands our knowledge, challenges our assumptions, and reminds us of the infinite possibilities that exist in the cosmos. The universe is vast beyond human comprehension, filled with billions of galaxies, each containing billions of stars, many of which host planets that might harbor life. We are just beginning to explore this cosmic ocean, and already we've found tantalizing hints that we might not be alone. The next few decades promise to be the most exciting in the history of astrobiology. New telescopes will study the atmospheres of potentially habitable exoplanets in unprecedented detail. Robotic missions will explore the subsurface oceans of icy moons. Advanced AI systems will analyze vast datasets for subtle signs of biological activity. Each of these endeavors brings us closer to answering the fundamental question that has driven human curiosity since we first looked up at the stars. Are we alone? The answer, whatever it turns out to be, will mark a new chapter in the human story. The chapter where we learn our true place in the cosmic community of life and intelligence that may span the galaxy and the universe itself.